Okay, then let's figure that out first. Okay, hello? Better? Okay, great. Good morning, everyone. Could you please get seated such that we can get started with the first session of today about representation learning and foundation models. And I'm Alessa Hering. I'm at Radboud UMC in Nijmegen, and I will chair the session together with...
I'm Bernhard Kainz. I'm professor at FAU Erlangen-Nürnberg and Imperial College London. Okay, if the first speaker would get ready, please. Is the first speaker here?
Yeah.
Good, come up. So the first paper is about capturing longitudinal changes in brain morphology using temporally parameterized neural displacement fields, presented by Ashia Shaibu.
Hi everyone. Okay. Hi everyone. I'm Aisha Lowell, and my talk today is going to be on capturing longitudinal changes in brain morphology using temporally parameterized neural displacement fields. So this work has been in collaboration with a colleague from the lab, Kieran Gibb, as well as my two supervisors, Peter Wijeratne and Ivor Simpson. So as we all know, neurodegenerative diseases are diseases that affect the brain. And longitudinal data gives us a way of analyzing specific morphological changes that occur over the time course of a disease. So what you're looking at here is this kind of an AD patient over the course of 9 months. And as is expected, we can see that there's ventricular expansion. That's expansion within this region here in the middle. And that's as a result of contraction from surrounding regions. So our data was gotten from ADNI, and alongside the Alzheimer's disease or the Alzheimer's data sets, we also got data sets from subjects with mild cognitive impairment as well as healthy controls. So in longitudinal analysis, we're looking for changes that are relatively very, very small, and these can be confounded to, quantifying these changes is confounded to many factors, including noise in the image. So in the case of noise, we have to somehow decipher if what we're looking at is actual shape change or if we're just looking at random noise. We have some other factors such as spurious changes that arise from image distortion from the scanner, or even sparse longitudinal data. So all these pose a huge problem in longitudinal analysis, especially because of the scale of what we're trying to quantify. So when we're making inference from our data, there are specific desired properties that ideally would want whatever machine learning model that we want to be able to derive from whatever machine learning model that we have. And some of these properties are that we want our model to be robust to noise, or we may want to be able to predict cognitive decline over a period of time. So basically, we want to be able to see what the brain scan looks like at different points in time. And more importantly, we want to be able to learn biologically plausible patterns. So for instance, if there is expansion in a particular region, we want that to be consistent over time. We don't want a situation where we have expansion and then sudden contraction, because that's not biologically plausible. So in Alzheimer's disease, we don't expect regeneration of tissues. So these are basically some factors that we somehow have to be able to incorporate to our model. And one way of deriving this is by using image registration, which is where my work comes in. So I'm sure most people here are familiar with image registration, but basically it's an alignment problem. We're trying to align two images together. And looking at it from a longitudinal registration perspective, what we're trying to do is we're trying to move images from other time points to the space of the baseline image. And longitudinal image registration gives us a way of deriving the change in volume over time using the metric called the Jacobian determinant, which basically at each local region we can look at expansion, whether that region is expanding or contracting over time. So this is a very useful imaging biomarker, especially when we are dealing with neurodegenerative diseases. So looking at the objective functions, typically we have two competing objectives. The first one is a similarity term that tells us how well our images match. And because registration is an ill-posed problem, we have a large set of possible solutions. So we need to somehow constrain this using regularization. So we have that different registration methods occur. We have different registration methods, and some of them are optimization-based methods or even using deep learning approaches like convolutional neural networks. But more recently, we're seeing an emergence of implicit neural representations, that's like INRs, and they seem to be a more good alternative for our approach. So I guess yesterday we had like a brief discussion of, our keynote speaker gave us a brief introduction of INRs, but essentially what they are is they are fully connected neural networks that serve as a continuous representation of data. So what you're seeing here is that you would have X, Y, Z coordinates going into your MLP, and in turn we predict this, the intensity of a particular location. And they have been used in lots of different contexts, such as 3D applications, or even in image registration recently. And one of the main advantages of this such parameterization is that we're able to derive, or we have access to analytic derivatives of our outputs with respect to our inputs, which is one of the things that we leverage in as our main contribution to the loss. So what we're proposing basically is that we have an INR, and we want to be able to predict displacement fields that are that serve as a continuous representation in space and in time. So this is a depiction of our model, and as an input to the model, we have observed time points, images at observed time points, as well as their corresponding time. And in turn, our INR predicts displacement fields, as well as robust estimates of our Jacobian maps that serve as that are temporally consistent at this observed time point. So what you're looking at here at the bottom row is your Jacobian maps at different time points, and they represent local expansion or contraction at that region. So if you take a look at our loss function, we have that in addition to the similarity term and the spatial regularization we spoke about, we also introduced this temporal regularization that ensures that our displacement fields are consistent over time. And we spoke about the benefits of INR, which is this natural property that falls out of our INR, the ability to take the derivatives of our outputs with respect to our inputs. So that gives us access to this derivative of our Jacobian determinant with respect to time. So we use this to propose a new monotonic regularization that basically ensures that at each voxel we have a continuous trajectory. So when a voxel starts to expand, that has to expand over time, or when it starts to contract, it has to contract over time. So this law basically just penalizes that. And we have that this property represents the rate of change over time, and it can also serve as a useful imaging biomarker. Our model is also able to interpolate and also extrapolate beyond the last observed time point. So now that we've defined our model, we can then derive Jacobian maps. We can predict the Jacobian maps for different groups. So here you're looking at the Jacobian map of a control subject over the time course of 2 years. And the changes are quite subtle because we don't really expect drastic changes for a control subject. But when we look at that of MCI, which is mild cognitive impairment, we can start to see that we can start to basically observe more apparent contraction and expansion within regions. And one thing to note is that in addition to our interpolation, we are also able to extrapolate while remaining temporally consistent. And finally, looking at the Alzheimer's subject, we can show from our Jacobian maps basically that we observed more rapid degeneration of our structures. So in red here, you can see that the ventricles expand and surrounding regions contract as a result. So we also looked at this across a handful of subjects. So what you're seeing here is the mean Jacobian, which is a measure of volume change plotted against time for different groups and looking at different structures as well. So we can see basically that there's an accelerated degeneration of anatomical structures, especially when we're looking at the lateral ventricle, and it's easier to see in the ventricles because it's a larger region. And now if we zoom into a single subject across time points, what we're trying to do in this experiment basically is we want to see the effects of our proposed monotonic regularization. So we look at the hippocampus for a single subject, and we at the y-axis here we plot the rate of change, which is the useful property that we spoke about, over time. And what you can see is a voxel-wise rate of change over time. So in the hippocampus, we observed that for each voxel either expands or contracts by a degree of 5% per month over the time course of the disease, which is very unrealistic because while we do expect change in the rate of change in the disease, or in Alzheimer's disease, but then we don't expect it to be this drastic. So basically what this is saying is that most of what we are seeing is noise. And then when we introduce monotonic regularization, we can see that that is more consistent over time, and it gives us a rate of change that's 20 times less than without the monotonic loss. And one thing to also point out that here is that on the left plot, you can see that the voxels, you can see that the voxels expand and contract over time, which is not biologically plausible, basically. So you can see like an up and down over time, which is not biologically plausible. So we can take a look basically at a different region. So here is the ventricle, and similar to the previous slide, what you're seeing is the trajectory of the voxels over time. And on the top row is without monotonic loss, and we observe that there's discontinuities as a result of erratic changes in the trajectory of the voxels. And if we compare that with monotonic loss, basically you can see that this is a smoother transition. So earlier on, basically, we spoke about how noise is a major challenge in imaging, and how somehow we need to decipher whether what we are looking at is actual shape change or if we're just looking at noise. So what we did in this experiment is that we applied different levels of noise to our data, and we looked at two main properties. The first was the mean Jacobian determinant, while the second was this rate of change. And as you can see on the left here, the plots basically show that there is high sensitivity to noise, and we don't really see a biologically plausible pattern. But with our monotonic loss, we can see that basically that we are able to predict more transformations that are more consistent with what's expected in this disease. So in conclusion, basically, we've seen that we have lots of challenges in longitudinal imaging, and we propose a method that uses an INR to be able to capture continuous, there's a continuous representation both in space and in time. And we also propose this new monotonic regularizer that could serve as a useful imaging biomarker. And in future, we're looking to do more validation because most of this is all qualitative, and we plan to extend this to other longitudinal data sets. Special thanks to my colleagues in the lab and Sussex AI, and thanks for listening.
Thank you. We have time for 3 exciting questions. I know it's early. If there is no question yet, then I'll probably start with one. So this is within subject.
Yes.
Would there be any way to expand this to population level or cross-subject disease modeling?
Yeah, so
what are your thoughts?
Yeah, so this is within subjects. One thing to note actually with an INR is that you can basically you fit one INR to a data, right? So you can't really do that across population, right? But then there are methods that have actually shown that you can do some population analysis and then you end up doing like a fitting for the entire population, right? So for instance, here what we're trying to do is we're trying to learn the trend of what actually happens given a particular population, say AD or MCI or control.
Okay. Please go ahead. Just speak up. I can repeat the question if need to.
I have one key question. Maybe I have it this, but as far as I understand, the INR needs to be converted for each individual case. In your test, how long does it take for the INR to convert it in a single case?
Yeah, that's a good question. So if we were not optimizing if we're not considering the analytic derivatives, right, INRs are very fast because basically we're just looking at linear layers, right? And if we have, say, 215 nodes going on and 5 layers, that's not much parameters to optimize. But because we were doing analytic derivatives, it took about 90 minutes to optimize for a single subject. Yeah.
Thank you.
Okay, yeah, final question.
Hi, thank you for the presentation. I'm interested in the extrapolation ability of your method. Have you ever tested it? And we know extrapolation is harder than interpolation. Can the model perform consistently, and is there any plans to validate it?
So we did evaluation where I have a poster session where that actually shows the results of like when you extrapolate. So we did an evaluation where we took out the last time point. Say we have observations of 4 time points at say 0, 13, month 14, and month 24. So we took out the last one and then we extrapolated and tried to get the residual. It doesn't do as well with interpolation, but one of the reasons was probably because of our time embedding. So we're also looking at doing more evaluation with regards to extrapolation, but it doesn't work as well as interpolation does work.
Only if you're quick, Matthias, very quick.
Quick question. You mentioned that you could speed up with amortized learning. Do you want to expand a little bit on this?
Yeah, so I think one of the methods that I think came from your lab last year was like using meta-learning to like learn the effects of whatever it is that you're trying to learn in that case. So that's one of the areas that we're looking to, basically that's using the reindeer or hyper network. Yeah, exactly. So yeah, we're looking to do that as well.
Great, then let's thank Aisha again.
Thank you.
And then we move on to our second talk, Loto's Latent Outpainting Diffusion Model for 3-Dimensional Ultrasound Stitching by Zhang Zhao. Floor is yours. Should I help you? Or?
Yeah.
This one, right?
Yes.
Please go ahead.
Hello, everyone. I'm Xin Yao. Today, I'm glad to be here to introduce our work, LOTUS, Latent Outpainting Diffusion Model for 3-Dimensional Ultrasound Stitching. So let's start with some background. Ultrasound stitching is commonly used in multiple diagnostics. However, it is challenged by limited field of view. So, for example, in prenatal imaging, as the pregnancy progresses, the placenta and the feathers becomes too large to fit in a single 3D field of view. So we need to move the probe to collect multi-view images to see the entire anatomy. In the figures, we highlighted the feather heads and the placenta, and we can see these two images are only partially overlap with each other because of the probe movement. In this situation, we want to align these two images to get a comprehensive field of view. This is ultrasound stitching. However, the common used registration tools such as Grady and ANS doesn't work well on ultrasound stitching. For example, here we have a pair of 3D ultrasound images. When we run Grady to align the source image onto the target image, it produces poor results. To make it easier, we add a initial composition rotation to the source image. However, we can see that the Grady even reverses the composition rotation back. This happens because the Grady is tends to match the sector-shaped field of view instead of the content, lead to it stuck in a local minimum. So we're asking, if we can fix this field of view affection by outpainting the image to be rectangular field of view, like highlighted by the blue text. And the answer is yes. After outpainting, the restoration performance is dramatically improved. Now the question is, how can we build up such an outpainting method? In the context of medical image outpainting, Gao et al. Proposed a GAN-based outpainting framework for 3D MRI. And Lehman et al. Proposed a diffusion model for 2D CT outpainting. However, both of these methods need whole image as ground truth. For ultrasound, the current work mainly focuses on 2D images. EcoGAN can outpaint 2D ultrasound from a smaller angle to a larger one, but it can't go beyond the existing field of view. Our previous work, SynStitch, can generate new content, but still within the sector-shaped field of view. 3D ultrasound outpainting faces multiple challenges. First, unlike other medical image modalities, the 3D ultrasound outpainting lacks of a whole field view ground truth. It's also hard to adapt existing 2D methods to 3D due to heavy computational burden. And recently, diffusion model dominates the image generation area, but its influence in image space is very slow. To solve the above challenges, here we introduce LOTUS, a test-time latent outpunting diffusion model for 3D ultrasound images. And Lotus works in the following steps. First, we train an autoencoder to compress images into a 4 times smaller latent space. We then train a diffusion model on the latent features of rectangular field of view patches to ensure that the model learns to generate latent features related to the rectangular shape. As inference, we encode the input image into latent space and extract the content-only features by the latent mask generator block. Then we output in latent space and finally decode it into a rectangular field of view image. Now, let's go through the step one by one. First, during the autoencoder KL training, we applied random affine transformations and cropping to the input to prevent overfitting and enhance the generation ability. And as you can see, there is a strong spatial correspondence between the latent space and the image space that enables the effective pixel space outpunting through latent operation. We also use a patch-based discriminator during training to help the model produce more realistic image. After autoencoder, we can train the latent diffusion model. We first upsample the images, followed by applying a random affine transformation, and then extract a central patch. This patch is then used to train the latent diffusion model with a standard diffusion process. And after training, it can produce latent features that can be turned into images with a rectangular field of view. And the Lotus can output in latent space during inference. Given an input 3D ultrasound image, we first extract its foreground mask by thresholding. Next, we encode the input into its latent representation. The latent mask is created by latent mask generator block. We firstly downsample the binary mask to a size that is smaller than the latent size, and then we pad it back to latent size. By applying this mask to the latent feature, we can extract important content features while removing the unwanted sector shift related features as highlighted in the red arrow. Later, we will output the removed area. In the following content, we call the kept content the kept area, and the part we want to output the outpunted area. The latent outpunting starts by adding Gaussian noise to the kept area. At the same time, random noise is passed through the pre-trained diffusion unit, which predicts a denoised latent feature in one step. We then combine the kept area with the predicted outpunted area. And this combined feature is then used as the input Gaussian in the next iteration. We repeat this process multiple times, making the outpunted area looks better. We'll keep the kept area unchanged. And finally, the outpunted latent feature is decoded into an image with rectangular field of view. Before we show the results, here's a quick look at the dataset we used. We used 2 in-house 3D placenta ultrasound datasets that were acquired by our collaborators at Penn. GenUS has 99 scans split into training and validation sites. And RegUS had 2 scans per subject for 20 subjects. Each pair is registered both ways, giving 40 pairs. We also measure their rotation and translation ranges. We divided these pairs into typical cases and hard cases. Hard cases have large rotations, big translations, or poor image quality, making them more challenging. The ground truth registration were manually done by 2 raters and checked by 3 more raters. Here we show correlative comparison on outpunting. Here we have 3 examples, each with its latent features and reconstructed images. You can see each image has a large blank area to fill in. And first, let's look at Lotus. It realistically outpunts a rectangular field of view. We have 2 baselines. Repent is originally a test-time outpunting diffusion model designed for 2D nature images. Here we modify it for 3D ultrasound outpunting. You can see the repent show visible artifacts between the outpunted area and the real image. The Lotus without the LMG module also struggles with high contrast edges. The Lotus works well because latent space outpunting with the LMG module removes unwanted boundary-related features and generates realistic details in the surrounding area. We also show the outprinting performance on the varying mask sizes. The OW is the outprinting window size. The task becomes more challenging with the decrease of OW. And as you can see, our LOTUS can open the image with realistic structures, even though in the hardest cases. Here we compare LOTUS and reprint in different OW. And we also compare their parameter size and the inference time. You can see LOTUS not only significantly outperform reprint in outprinting, but also dramatically decrease the parameter size and speeds up the inference about 40 times. Here we show the qualitative comparison on a typical case example. In the figure, each row represents one imaging plan, and our target is to register the source image to the target image. As highlighted, before the outprinting, the algorithms turns to match the field of view instead of the content, result in bad performance. In contrast, using LOTUS outprinting as input, both greedy and ends consistently achieve accurate registration. And for quantitative evaluation, we firstly compare the registration results with a fixed image on the overlapping area. We can see both greedy and ends show moderate improvements. In contrast, the proposed LOTUS-based methods significantly outperform their counterparts. And interestingly, LOTUS ends even outperform the manual ground truth. The death score here is just to measure how much the field views overlap to avoid the trivial solution that only reduce the overlap area instead of matching anatomy. We also compare the registration results with the manual registration ground truth. Besides the similarity matrix, we report the transformation error to provide a direct measure of registration accuracy. The LOTUS significantly outperforms its counterparts across all metrics. Then let's see the registration results on hard cases. As highlighted by the box, we firstly introduce an initial composition rotation that ranges in 10 to 30 degrees, noted as CR, to the moving image. You can see both baseline methods failed due to the strong local minimum. These methods even reverse the initial CR back to the identical matrix. In contrast, LOTUS-based methods leverage the CR initialization to refine the registration and successfully align the images. The qualitative results show the similar trend. You can see the LOTUS-based methods consistently outperform their counterparts across all CR levels, and with their advantage becoming more obvious as CR increases. To draw the conclusion, in this work, we propose LOTUS, the first model that can open the 3D ultrasound from sector-shaped field view to rectangular field view. LOTUS can achieve realistic results, will dramatically improve the inference speed with lower computational costing compared to its image space counterparts. And with the field view outprinting, we overcome the local minimum inflection and significantly improve the registration performance. There are many thanks to the MIDL 2025 organizers and our collaborators. And please feel free to follow our Twitter and check our code on the following GitHub. Thank you.
Thanks. Thanks for this very nice presentation. The floor is open for questions.
So very nice talk. I'm trying to understand what you're doing. So the ultrasound image is a sector or cone, and you're outpainting or synthesizing what's outside the cone, right? So it's not related to what's actually in the patient. It's filling in a realistic anatomy to make a rectangular image.
Yes. Yep.
Okay.
Now we're all awake.
That's so close. Yeah.
In a clinical perspective, I don't know how clinicians would really like to see an image in which the part of the image outside the sector is synthetic. Do you have any thoughts about that?
Yeah. So that's a very good question, and we also think about this in two aspects. Firstly, so in these methods, we tend to keep the original anatomical area unchanged. That's because they are important for clinician diagnostics, and we don't want the synthetic methods to change any part of the important anatomical structures. And output the outside area is, it's just you can regard it as a pre-process for the following downstream registration task. And actually, what we do is, during the registration, we output the image first, input them, get the fine transformation, and then we apply this transformation we learned directly to the original image. So in this case, actually, in the final registration results, we don't need to see this outprinted area. That's the first aspect. But on the second aspect, we are also targeted to outprint. In the future work, we also targeted to outprint some realistic structures, maybe have some clinical meaning, outside the area. So in this way, this method can be utilized as an augmentation method for some downstream tasks like segmentation or registration. But can it answer your question?
Thank you.
Thank you.
Is there any other question? Otherwise, I have one. I was wondering about the type of registration you are using and how that affects the performance that you need for the outpainting. So when you use rigid versus deformable, and what makes more sense for this task, because you do have not only translational error but also more movements in it, and therefore a deformable registration would be more feasible, I guess.
That's very, very good question. So also two aspects. So first, regarding rigid and deformation, here we only focus on the, a fine or rigid. That's because, according to our clinicians, they more want rigid transformation because the initially to ultrasound image has a very large rigid transformation between their anatomic. And after we align this, we fix this rigid transformation, they can identify what is what, and they can do the following registration by themselves. On the other hand, if we do deformable registration, we may distort some important structures. That's what we don't want. That's the first part. And the second part is, besides this is based on intensity-based registration, but we also have key points-based and other types of registration. And according to our formal study, which called SynStitch, we find the sector-shaped field of view also influence the key points-based registration. They may focus on the edges, not the contents, because edges has a very high contrast. So these methods may also help with this part. Can this answer your question?
Yes,
thank you. Yeah.
Then let's thank the speaker again.
Okay, the next paper is Duoformer, leveraging hierarchical visual representations by local and global attention, presented by Xia Ya Tang. Is it you? Yeah, Xia Ya Tang.
Okay. There's now searching the full screen mode. Thanks. You unfortunately don't have it mirrored here.
So, hello everyone. My name is Xiaoya Tan. I'm from University of Utah. Welcome to the Utah. I'm very happy to present our work about learning local and global representations in Vision Transformer today. In this talk, we will go through the background of Vision Transformer, our motivation, model design, and our key findings. So first, let's talk about some background. So this chart shows the progress of top-performing models over the past decade on the ImageNet classification benchmark. Since 2020, when Transformers was first applied to visual tasks, it has surpassed the previous state-of-art models like ResNet and becoming very popular on various vision domains, including the medical images. This chart from 2023 give us an intuitive sense of the growing momentum of VITs on medical image data. So this highlights the VIT's potential to handle diverse data modalities. This is a very simple illustration of a vanilla vision transformer architecture. So So the input is a sequence of image patches. These patches are then transformed into vector representations, which we call tokens, by a patch embedding layer. And these tokens are then fed into a stack of attention blocks. So after that attention, the output is also a sequence of tokens. And then what is special here is we use a COS token, which is a placeholder we usually put in front of the input sequence. So after the attention, this COS token is used for our prediction. And empirically, people found that the COS token can capture a good summary of our whole input sequence. So that make it highly useful for tasks like classifications that requires only sequence level understanding. We utilize these characteristics in our design of the local attention module. So from previous slide, we know that VITs has a uniform patch embedding. So people has also found that they have some less local receptive fields. We can see on the right figure, we see the mean attention distance across 24 layers in the VIT large model. We can see some attention has already captured global information very early, even in the first few layers. But this is different from CNNs. You can see the blue area, the receptive field of a CNN grows slowly and linearly. This observation has also been confirmed in another study. From the right figure, we see the ResNet's receptive fields are highly local, especially in their early stages, which is different from VITs. So these characteristics raise the main challenge in vision transformers, that is their lack of inductive bias, mostly around lack of locality, which means that they can only learn the important inductive bias purely from the training data. So that makes it challenging when adapting to medical data because a large data set is not easy to obtain. So how do people solve this problem? We categorize those related works into three main directions. First is incorporating CNN and utilizing hierarchical structure, which are believed to be beneficial for vision transformers. And another approach is to design window or local attentions. But this method share a same limitation, which is they either use a fixed size downsampling or confine the attention inside a fixed sized window or a local kernel. But this can be suboptimal for medical images, especially come to the histopathology images. We can see from this figure, in those histopathology images, the visual entities are always appearing at various scales, and they share very similar appearances. So we aim to design a model that can flexibly attend to different scales as the task and our data need. This is how we solve it in the Duoformer model. So this illustration gives us our proposed multi-scale patch tokenization process. In this process, we utilize a pre-trained CNN backbone to produce multi-scale feature maps from their lower and higher stages. So in the vanilla VIT, we usually split an image into 16 by 16 image patches. Here, we split and take an image input size as 2 to 4 by 2 to 4. We split it into 7 by 7 here. And for every image patch, we see the blue cubes. We extract the feature representations from every scale, and we concatenate them to form a multi-scale representations. So because this multi-scale, we did this process for all the image patches. So because the multi-scale representation encodes a rich semantic information, that's enable us to use a coarser grid than vanilla VIT does. And then we propose a specially designed scale token here. So this mimics the characteristic of CLS token, which is also a placeholder we put in front of the token sequence. But different from CLS, this is not initialized from random, but fused, derived from the same hierarchical representations we previously used. So this is how we did this by simple projections. We utilize a simple convolution layer to project the feature map from every stage, and we concatenate them, and we use another convolution layer to project the results into a vector representation, which share the same dimension to our multi-scale tokens. And then we concatenate the scale token in front of our multi-scale tokens. This component can be beneficial if you are using transformer architectures and can be plug and play. And then we, the multi-scale token sequence incorporate an additional dimension for scales that enable us to use the attention directly on this dimension. We call it local attention. So after the local attention, we assume the scale token carries detailed information from all the scales for every image patch. So we pass only the scale token into our next attention module, which we called global token, global attention. And before the first global attention layer, we also add a CLS token in front of the scale token sequence. And after the global attention, the CLS is used for classifying. To make things more intuitive, we draw an illustration to show the roles of the two attention types. The blue arrows represent the local attention. So inside the local attention, every area is able to attend to their local representations from all the scales. And in the global attention, which the blue arrow shows, the model can learn a holistic understanding from all the areas. This is how we did it. And we used two pathology data sets to evaluate our model. There are both for the most common type of kidney cancer. And we evaluate our model under two different scenarios. One is that we train the backbone with our Duoformer together. And another one is we freeze the backbone, which is unsupervisedly pre-trained on pathology images. And the two tables shows our model can efficiently harness multi-scale features and integrate crucial inductive bias. We also did a lot of ablation studies to validate the effectiveness of the proposed component of us. We found that on both datasets, the combination of local and global attention performed the best. And then for the scale token, we found that it is, if we use the first token in the multi-scale token sequence, it can perform comparable for our proposed scale token. That means the first token can also carry an important summary of the whole sequence, but our scale token is still better because it can efficiently fuse the multi-scale information by projections. And then another finding of us is that, do we always need as many scales as we need? Intuitively, we might think yes, we can always benefit from more scales, but we did a thorough study on both datasets to test all the combinations of scales. We found that this is not the case. We found that the optimal combination varies between datasets, and also influenced by the dataset size and potentially by the scales of our targets. So our key takeaway is, so our model can attend flexibly to all the scales as our task need. And then in the future, we want to incorporate with token pruning and other sparse attention mechanisms to further improve our model. And we have 2 more posters to discuss different use of multi-scale features on ECG diagnosis. Welcome to stop by and discuss with me. Thank you for listening.
Thank you very much. We have time for one question. Any questions? Can you perhaps comment a little bit on the computational overhead in comparison to something like a swing transform?
Yes, it is a very good question. We acknowledge that incorporating one additional scale always cause some computational overhead. There's always a balance between our computational cost and the performance gain. And we provide actually, this is one of the reviewers' question, and we give a theoretical analysis. Our model is actually a constant time of VIT DAS, and we also gave this actual training tab in our paper. If you are interested in, please refer to our paper. Thank you.
Okay, thank you very much. Let's thank the speaker again.
And then we continue with the next talk on segment anything for histopathology by Titus Gabriel, but I think presented
I'm the one presenting.
Yeah. Anweit.
Okay, let's get started. So, hello everyone, I'm Anway Archit. Am I audible? That's all right? Perfect. I'll be presenting segment anything for histopathology today. And my presentations are usually like a story time. So let's get started with the story. So on a normal day, why do I need segmentation in histopathology? So this was one of the discussions I had with the pathologists when we were getting in the loop of some of these projects with segmentation. And I had one of these questions wherein they addressed a challenge that they had a lot of H&E slides just lying over there. And they had a particular pathology. They had graduation period about the entire pathology structure for multiple patients, multiple cohorts. And they started asking me a few questions you see over here, wherein they wanted to, to take a step back, quantify different things so that they can understand some mechanistic modeling or some structures about something in the whole slide images. And this is how a usual workflow in the lab would look like. One would first image a histopathology scan, and then they would first start to visualize on a crop level, extract a small crop, get segmentations for each of the nuclei, try to recognize the class for each of the nuclei, and then do some quantitative analysis on top of that. And doing this manually on such gigapixel images, it is a nightmare. So how do they approach this? Do they really paint all of these cells for 8,000 whole slide images? No. The starting point is often with the current deep learning era with automatic segmentation tools. So there are 3 popular names over here. The list is quite exhaustive. And then let's say if these methods are not something what fit for them or something which doesn't work for their data, how do they approach this problem? So in those cases, they fall back to the classical interactive segmentation. And here are 3 examples of a bit more advanced version of that, wherein you can develop a workflow for yourself and make your interactive segmentation schemas faster. But then you see a very obvious problem here. There are 2 different pipelines, and you might have to go back and forth to do exactly the same task for every new patient. And the limitations are quite obvious, as we see. The worst quality for different data distributions compared to the training data really affects your downstream tasks. And it can change, like domain shifts can really, are in a spectrum, for example. They can change for image settings, for specimen reasons, for some staining attributes, stuff like that. And every time you have to go through these workflow pipelines, you always have to annotate a lot of data. I mean, a lot. And application to a new data is always time consuming, because if you think about this workflow, you have to do this in a human-in-the-loop fashion all the time. One of the examples over here is HoverNet, which was trained on a large amount of data, and it does a pretty good job on images which it has seen in the past. But every time something changes in the imaging setting, these models just stop working. And here is where the plug comes, segment ending for histopathology, wherein we are trying to build a vision foundation model for histopathology image analysis. So let's take a step back and understand the cool segment anything work. So segment anything takes a user's input and lets you decide what you want to segment in over there by putting in a click or bounding it around with a bounding box. And then this is kind of a framework they innovated and created a vision foundation model for interactive segmentation. Now, what can segment anything do? So I would personally say segment anything is an amazing model off the shelf. And on most cases, you see over here, it does a really good job at zero-shot segmentation. What really interested us is they presented some results in microscopy, specifically for nuclei segmentation, and we were thinking, is it as good as that? And this is where we started investigating themes on the medical imaging aspect, to be precise here, in the histopathology domain. So how do they achieve such an amazing model? So what they do over here is have one of these unified model structures, and they allow user to provide an image, some context of what you want to segment without giving a random segmentation out of nowhere, and then helps you guide the model to segment the cat, for example, over here. And the way they generate, I think, so taking a step back, I think their major strength is the data curation aspect. Because by creating one of these mechanisms, they start really simple, train a small model, go back, use annotators to say, okay, these are some images. Can you please put points, clicks, or text to segment more stuff? And they do this in a human-in-the-loop fashion with a lot of annotators and generate a huge data on which they train their model. Now, how does the training design look like? We looked at the architecture very briefly. So a regular training would usually be you pass in an image, the model gives you an output, and you try to optimize or update the model so that you get better outputs in future. With segment anything, the training is pretty cool. So what they do is try to replicate how a human would try to segment things in an interactive design. So what they do over here is take an image, derive points or boxes out of it, and then put it into the model, and then see what are the outcomes coming out of this. So you get some segmentations over here. And then they do something which is called iterative prompting. What this basically means is you let the model know what mistakes or what, let's say, good things it did, try to make more rectifications on that aspect, and retrain the model for this objective for n number of times. Now, out of all of this, we started to think, how does it work off the shelf for histopathology? Over here, there are very few examples wherein you see if the nuclei is isolated from, it's not touching other nuclei or it has a very good contrast, segment anything does a really good job. The automatic segmentation is a different story, but they do a very simple heuristic over there, which is not so relevant for medical imaging tasks in general. Now, we started thinking, can we improve this? A quick spoiler is yes. So what we see over here is if we fine-tune the model with a heuristic, which I'll talk in a second, the model improves quite a lot and becomes, let's say, contrast agnostic or even task agnostic in some cases. And there is one of our contributions for automatic segmentation, wherein the quality with just a click of a button does a really good job. So what was our goal over here? Our goal was to evaluate and improve SAM for histopathology. And our focus was to present exactly what Segment Anything dreamed about, having interactive segmentation, extending it to automatic segmentation, having both in one model. And this is what we tried to do. And the training procedure was implemented by another work, Segment Anything for microscopy, which we call MicroSAM here. And if you see the top part with bold arrows, that's the contribution from MicroSAM. We extend the architecture to do semantic segmentation over here. The color aesthetics are bad, I'm sorry. But this is the semantic segmentation decoder, which can classify the nuclei on top of identifying them individually. Now, how do we improve this for nucleus instance segmentation? We assembled a large amount of data, precisely large amount of open source data, which had a lot of images across several, let's say, staining. For training purposes, we only used H&E stained. We fine-tuned SAM on this particular data set, and we evaluated quite extensively. One of the examples you see over here is for interactive segmentation, wherein we see if we compare it to the microscopy generalist models or even the Segment Anything model, our PathoSAM model, which is the pathology-specific model, does a really good job in identifying nuclei. And we see this improvement quite sharply for very weak prompts. So a single point or a single box would be a usual focus, because on a normal day, you wouldn't want to rectify each and every nuclei for all the whole slides, right? What we see over here is the automatic segmentation quality. And there are a few methods presented here. There are a lot over here what we are benchmarked with. But what we notice is if we compare it with CellVIT, which we believe is the current state of the art, we see that PathoSAM really generalizes well, even in very different imaging conditions. And what you see over here is one of the plots where we compared all the models. And we noticed that in most of these cases, if you're familiar with this, HoverNet, StarDist, CellVIT, most of these models have, most of these methods offer multiple models. So as a histopathologist, you really have to choose which automatic segmentation you want to opt for. But with PathoSAM, you don't have this trouble. Despite favoring all the other models by choosing the best model per data set, PathoSAM is one of the universal models which works for automatic segmentation and proves to be the current state of the art. What are our further contributions here? So we extend PathoSAM to do semantic nucleus segmentation, as we discussed. We also allow users to fine-tune their own model if there's a different structure where the model just does not work for you. One of the examples is for gland segmentation, and we saw that the model translated to this task pretty well. We allow users to do whole slide inference in a batched format. So this takes a couple of minutes, and it will give you amazing segmentation quality. And we allow integration, or we actually integrated our tools or our models with QPath and MicroSAM, so users can use this pretty awesome, like in an interactive way. There are limitations, all fancy and all things discussed now. So semantic segmentation is still not at par to the current state of the art we consider. And the most important factor to consider over here is, like, let's say CellVIT does class balancing for that particular task. And in general, the current methods do not generalize as well for different classes. So how would you go beyond 4 classes, for example? And there is quite a bit of an outlook for our project, which we are looking for. But the higher level outlook is we want to create a vision foundation model, which is scale invariant, which can work for tissues, glands, nuclei, pretty much anything. And that would be me for today. Thank you so much for listening.
Thank you so much for this talk. The floor is open for questions. You have one. So your lab already published the paper, segment anything for microscopy, and now
Yes.
the one for
Histopathology. Yeah.
Thank you.
Yeah.
I was wondering, do we now have one paper after each other for all the different modalities?
So that is actually what we observe, that if you try to create one model for everything, this is really difficult because the domain shifts are so far away that creating one model it's a bit ambitious. But we have something working under the hood now, which will unify this very soon.
So there is then one strategy behind it that can be applied, but you still have to fine-tune
Exactly, exactly. So we kept the theme or the principle the same, which is why the training procedure comes from MicroSAM. We didn't touch anything over there, but just adapted it for histopathology.
Okay, thanks. Please go ahead.
Thank you for the presentation. Very good, right? So one quick question for your evaluation. You mentioned in the slide you use the average accuracy. Actually, it's not very common to just use the accuracy to evaluate the segmentation for histopathology images. Usually people will choose to use object level or instance level evaluations, right? So because you have the average overall probably cannot tell the case, right? So because it's an instance or semantic segmentation, you have to match out there, right? So do you have some insights or do you have some other results that you did?
So the metric you see over here is mean segmentation accuracy, and it comes from the Pascal walk challenge, which is devised for instance segmentation, wherein you compute the area under the ROC curve for IOU precision over 50% until 95 and average over all of them. So it's a very hard metric if you try to compare. For example, if you saw, the best method was still 40%. So if you think about it in perspectives, 40% might not seem good, but it also considers IOU 95%. So that overlap is a very strong overlap, I would say.
Yeah, even though you use IOU, you use the overlap, but still, you cannot use the overall IOU, right? You have to use the instance level IOU.
This is what we are doing. We are doing on an instance level, always. Because without that, it doesn't make sense. You don't know the instance segmentation quality.
So you are talking about your accuracies based on the object.
Yes. It's just the name which is coined from the Pascal walk challenge because it's a very standard name. I'm sorry for the confusion.
Thank you.
Then let's thank the speaker again.
Okay, very good. And let's get to the last presentation of this session, which is vector representations of vessel trees, presented by James Batten.
So hi, my name is James Batten. I'm a PhD student from Imperial College London. So today I'm going to be presenting our paper called Vector Representations of Vessel Trees. In this paper, we describe a model called Vessel Tree Transformer Autoencoder, or VETA. This research focuses on learning compact vector embeddings for complex tree-structured anatomical data, such as vascular networks, using transformer-based autoencoders. This work was done in affiliation with Heartflow, who provided the data and the computational resources. So the core challenge we're addressing is how to encode highly complex tree-structured anatomy, such as a patient's unique vascular network, into simple compact vector representations. Every patient's coronary arteries, for example, have variable branching patterns, shapes, and curvatures. Traditional methods struggle with this variability, but compact vectors could enable better integration with downstream tasks like hemodynamic analysis or disease diagnosis. So current approaches like grid-based models or convolutional autoencoders have significant limitations. For example, 3D voxel grids are memory-intensive on GPUs, requiring post-processing to extract meshes and centerlines. Discrete grids often lose fine geometric details crucial for coronary analysis, and reconstructions have artifacts like disconnected components or shortcuts. Our method aims to overcome these by directly encoding continuous geometry and topology. So our proposed method, VETA, employs a two-stage approach. In the first stage, a vessel autoencoder encodes individual vessel segments as vectors, capturing their continuous geometry from sampled points along the centerline. In the second stage, it leverages these segment-level vectors to encode the full tree, including its discrete connectivity, as a single unified vector. In the second stage, a recursive decoder ensures a valid tree structure by design, building the topology step by step to avoid invalid configurations like disconnections or cycles. In contrast, the first stage decoder focuses on continuous vessel representations, which preserve the geometric precision of individual segments. Additionally, transformers in the architecture in both stages capture long-range dependencies across the structure, allowing the model to handle branching patterns and maintain overall coherence in the embeddings. As mentioned in the previous slides, in stage 1, we focus on encoding individual vessel segments. The input consists of 64 points sampled along the vessel centerline, where each point includes spatial coordinates x, y, z, and the local radius r. To capture high-frequency details, we lift the position coordinates to the Fourier feature domain using sinusoidal embeddings. We also increase the sampling density in regions of higher curvature to better represent tortuous vessels. For the output, the decoder acts as an implicit representation, conditioned on the vessel embedding ZV and a parameter t between 0 and 1. This maps the interval from 0 to 1 onto a continuous reconstructed curve, ensuring smooth geometry. We guarantee that the decoded vessel precisely attaches to its endpoints by adding a residual term to a simple linear interpolation between them, with a masking function that enforces exact matching at the start and end. In stage 2, we build on those vessel segment vectors to handle the full tree structure, ensuring topological consistency through recursive decoding. Starting with the encoder, the model takes the direct edges of the tree's connectivity as input, along with the vessel segment embeddings from stage 1, and pulls everything to a single global vector, ZT. This happens in one efficient forward pass, as illustrated in the top diagram on the right, where the full input vessel tree is processed to produce ZT. The decoder uses a global embedding ZT plus the partially reconstructed tree as input, is trained to learn a single step of the recursive decoding process conditioned on the global tree embedding provided by the encoder. At inference time, the decoder rebuilds the tree node by node, starting from the partial output at step n, and then adding predicted nodes to reach step n+1. This recursive process is designed to always output a valid tree, preventing issues like disconnected branches or invalid loops, which makes it reliable for vascular networks. So this slide illustrates how VETA performs in terms of reconstruction fidelity on the vessel trees dataset. So this is a dataset of real vessels derived from CTA images. So we trained and evaluated the model in both standard autoencoder and variational autoencoder configurations, using subsampled coronary trees limited to a maximum root-to-leaf length of 60 millimeters. Since the VETA model is trained only on geometric information, it uses far less GPU memory than the 3D convolutional baselines, and can be trained with batch sizes on the scale of multiple thousands. VETA outperforms the baselines across key metrics in both the standard and variational autoencoded configurations. VETA achieves better reconstructions than the 3D convolutional baseline on test trees. Vessel VAE, which is more geared towards generation than reconstruction, shows weaker performance here. Qualitatively, the images on the right illustrate this. The ground truth mesh on our left, proposed reconstruction on the right, and an overlay of the ground truth centerline in yellow, with the reconstructed centerline in red. You can see the close alignment, with VETA producing high-resolution, smooth, and anatomically plausible structures without artifacts like disconnections that are very common in voxel-based methods. So beyond reconstruction, this slide demonstrates the semantic coherence of VETA's latent space through interpolation experiments. In the variational setting, we linearly interpolate between the embeddings of two unseen validation samples and decode results at intermediate points. The top row shows 3D interpolations on real coronary vessel trees from our vessel trees dataset. Starting with the leftmost structure, you can see a smooth morphing to the rightmost one, with gradual changes in branching and curvature while keeping the overall anatomy plausible. No hidden artifacts or invalid shapes. And for the bottom row, this illustrates a similar experiment on 2D synthetic trees from this SSA dataset, where the transitions maintain connectivity and branch patterns throughout. A major benefit of our recursive decoder is that it preserves valid tree topology at every step in the latent path, unlike baselines that often produce disconnected or malformed structures during the interpolation. To further illustrate this latent space coherence, this slide compares interpolations on the 2D synthetic tree dataset between our proposed Veta VAE model on the top row and a baseline CNN VAE on the bottom row. So both are variational autoencoders, and we're linearly blending the embeddings of two validation samples and decoding at steps along the way. So in the top row, our Veta model produces the smooth connected transitions with the valid tree connectivity at every point. And the branches evolve gradually without breaking or forming invalid structures, thanks to the recursive decoder enforcing topology. And by contrast, the bottom row shows the baseline's interpolations, which rely on segmentations and often result in disconnected components or fragmented trees, losing the coherent structure midway. So this comparison on synthetic data underscores how our method maintains anatomical plausibility during latent traversals, unlike the convolutional approaches. So in conclusion, our proposed Veta model effectively encodes and decodes coronary artery trees. I do have the conclusion slide. And delivering high-quality reconstructions on unseen test data, as demonstrated by superior metrics and visuals compared to baselines. Additionally, our latent space exploration experiments reveal that the model produces semantically coherent interpolations between test samples, maintaining valid topologies and plausible morphologies. So that said, there are some caveats. The model is relatively slow to train, taking about 12 days on a single V100 GPU, and it relies on large volumes of training data. In our case, it's 4,000 full coronary trees from HeartFlow's dataset. So we'll release all the code to train the models on GitHub, including the checkpoints on the synthetic data. Thank you for your attention. Happy to take any questions.
Thank you very much, James. We have time for questions. Are there any questions from the audience? Yes, Ron, please go ahead.
Okay, so if I understand correctly, your encoder is encoding the topology as well as the curvature and the radius of the vessels throughout the tree.
Yep.
So an application that I'm interested in is non-coronary arterial segmentation in the abdomen, and where the vessels might have very small diameters. I imagine you have a similar situation on brain angiograms.
Yep.
Can you talk a little bit about how well your method would do in noisy data and where the blood vessels are small?
Yeah, so for the dimensions of the blood vessels, I think it still works the same because this is a model that's trained on the geometric information. So the scale, there isn't really a scale dependency there. That said, for the noise in the data, I think it would struggle there. This really does rely on having high-quality training data. So in HeartFlow's case, they do have a very large data set of very high-quality data that's been annotated manually by lots of analysts. I think if it's derived from imaging data where there's a lot of noise or it leverages segmentation algorithms that don't work very well in those modalities, then yeah, I think this wouldn't be the optimal approach.
Yes, please. Yeah. So if you can speak up.
You can shout.
I can repeat, or you take this mic.
So looking at the computational requirements of the current algorithm, I was wondering if any classical methods like the Crunchy vesselness filter or something that was more traditionally used for describing vesselness could be incorporated as an initialization point to reduce your training data requirement, or even as just a different set of features that get incorporated within the training.
Right, yeah. So again, if it is the case that high quality annotation data isn't available at scale, then there needs to be some sort of process that derives this geometric information from images. And there, yeah, I think it really depends on how much noise there is in those methods. Potentially that can also be integrated into the model, like into the vector representation itself as some sort of vesselness. But that would be quite a significant departure from the architecture that we're proposing. But yeah, interesting idea.
So I'm thinking not just in noisy cases, but even when you do have annotations, if you incorporate a different branch, which doesn't entirely rely on annotations, so it's almost two different information streams, and they both provide, there's a certain overlap of information, so that you might need fewer annotated images.
Right. So you're saying that, for instance, if you're in a situation where you have like some image data and also some partial annotations in that image, and then you want to complete that?
No. So the same set of images, we use a conventional filtering like Fremji Vesselness or something, and then we also have the matching annotations for the same, and we use both as inputs to the model.
Right. Yeah.
So then I think if both the computational demands might go down, as well as the amount of information that we require, so the amount of annotations that we require might go down.
Yeah. So from the moment there's like another pathway that's added that includes image data, then that representation contains qualitatively more information, and then yes, in that case, improving efficiency by adding things like SNS does make a lot of sense.
Thank you.
Okay, thanks a lot. Let's thank James again, and let's thank all the speakers of this session again, and this concludes this session.
We'll be taking a group photo out here now, so if you want to join us, please head out there.
Right, thanks.
Thanks, Sven. Anytime again.
Check 1, 2, 3. Check 1, 2, 3. Check 1, 2, 3. Check 1, 2, 3.
If you want your lunch in 60 minutes, better hurry and come here. Okay, let's get started. Good morning, everyone. It's a pleasure to introduce today's keynote speaker, Professor Mirabella Russo, a leading researcher in AI-driven imaging-based integrative diagnostics. Professor Russo is an assistant professor in the Department of Radiology at Stanford University, with courtesy appointments in urology and biomedical data science. She leads the Personalized Integrative Medicine Lab, where her team develops cutting-edge methods to fuse data from multiple imaging modalities, particularly bridging high-resolution pathology and MRI images with more accessible tools like ultrasound. Professor Russo's work enables earlier and more accurate cancer detection with a strong focus on prostate cancer. Her research has broad implications for improving care in both advanced and resource-limited settings. Her recent contribution in prostate cancer imaging have been featured in medical physics and medical image analysis, both advancing the state-of-art in identifying aggressive cancers using routinely available imaging, but also underscores the impact and translational potential of her work. Today, she will be presenting a keynote titled Multimodal Learning for Early Cancer Detection in Low-Resource Settings. So please join me in welcoming Professor Mirabella.
Shireen, thank you so much for the introduction, and thank you all for having me here today. Let's see if I can find my presentation. I need help, maybe? Where's my presentation? Here we go. Found it. No help needed. All right, here we go. All right, so thank you for the introduction, and more importantly, thank you all for inviting me here today. It is a great pleasure to talk to you about the research in my team and some of the things that we have learned as we are performing this multimodal learning research. So as Shireen mentioned, I am an assistant professor in the radiology department, and I have courtesy appointments in urology and data science, and that summarizes very well what I do. So specifically, I come from the perspective of I want to develop methods that will improve the interpretation of radiology images, because I am in the radiology department, but I also truly believe that the radiology images have a unique utility in clinical care, so I want to take advantage of that. And the way I go about doing that is that I develop computational methods, surprise, AI-based, very often, localizing cancer and distinguishing subtypes, aggressive and indolent being that type of subtype I look at. I like to use multimodal artificial intelligence methods, and then I also work, as mentioned, a lot on prostate cancer. About 90% of my projects are on prostate cancer, but very often I like to expand in other directions. And I'll talk a little bit today about some of our breast work, but as I said, 90% of the presentation will be on prostate. And it summarizes here, shows pretty nicely that I work on MRI, detect cancer subtypes, but also I try to bring these ideas and concepts to prostate ultrasound, which is a space that needs some help from the AI perspective. Why do I look at prostate cancer? Prostate cancer is still the most diagnosed cancer among American men, 20% of all diagnosed cancers. And that is not only in US, that is actually in other countries as well. Europe, it's quite common. Is the second leading cause of death by cancer in American men. That's about 10% of all cancer, because that's that common. So I would like to think about kind of the patient journey, and I like to refer to the patients as, let's say, the generic Mr. Smith. Mr. Smith will have some form of screening for prostate cancer, will have a prostate-specific antigen that is derived from a blood test, or some sort of digital rectal exam. If any of these are abnormal, this patient will go in what I like to refer to the diagnosis pathway. The diagnosis pathway involves getting a biopsy. This is guided by ultrasound, but because we kind of acknowledge that ultrasound is, yeah, good, it's real time, but it's not great in terms of quality. Clinicians have dealt with that by saying, okay, let's look at MRI. MRI has better soft tissue contrast. Let's look at MRI. Let's fuse the ultrasound with the MRI in order to guide this biopsy. If this biopsy the biopsy will collect a pathology sample. We'll see here a pathology core, and then if the patient, Mr. Smith, has a disease, he will undergo some form of treatment. I really like to look at patients that get surgery, because patients that get surgery get this beautiful data that I can correlate back to imaging. But acknowledging that that is definitely a biased cohort. In this context, we have seen MRI, and a lot of people do AI for MRI because prostate MRI is very good at guiding the biopsy. Nowadays, there are also local treatments that are relying on MRI and the ability to see lesions, and then they can do a local ablation of the tissue, so not the entire organ receives the treatment, which is good. It has less side effects and all of those. So MRI is great. It has a high accuracy, it has a good sensitivity. However, it's not perfect. Radiologists are still missing some cancers, and it really depends on which cohort you look at. But those numbers of how many cancer are really truly missed can range anywhere between 12 and 34%. But also more importantly, there are a lot of false positives. These are regions that a radiologist considers to be suspicious, but at biopsy comes back as being benign, so no cancer. So in this context, of course, that also means that the appearance of cancer is quite subtle, and that's the reason why it's challenging to actually find some cancers. And that also results, subtle features means when you actually compare multiple radiologists, they will disagree with each other. And then you can measure that how much variation is in how radiologists interpret these images, and those numbers can vary quite a little bit. And that kappa on PIRADS, which is the way radiologists look at these images, can vary between 0.46 and 0.78. And perfect agreement means 1. No agreement, it's kappa equal 0. So in this context, what my team has been working on is really working on improving the interpretation of radiology images. Can we help radiologists find these missed cancers? Can we reduce the false positives? And more importantly, also decrease the interreader variability. But I am in the space where I like to challenge. I like a challenge. And with that, one of the thoughts that I was thinking about is let's try to do something more than the radiologist does. And specifically, can we actually help them guide that biopsy needle towards the aggressive part of cancer? In this context, I set myself this challenge to not only detect the cancer, but really figure out in the cancer, which we know they're very heterogeneous, which part are aggressive and which ones are not aggressive, they're indolent. And with that information, I can help the urologist, which is the person doing the biopsy, guiding the needle not only towards cancer, but towards the aggressive part of cancer. So that's how I do it, and that's why I want to use pathology information to guide that process. So let's go into I'll go into that part, but the first lesson out of this few things that I just said is that you need to take the time as a trainee, student, postdoc, and faculty as well, but you need to take the time to understand the clinical need. And that has a lot of things that need to be understood. We need to sit down and think about the big picture, how our AI approach is going to affect the clinical care, and also the nuances. Where is this algorithm going to be used, right? And I had here a couple of other things that actually I think is very important as you're developing these AI approaches is think about your user. Your user are the clinicians. Shadow them. See what they do every day. See how much time they spend doing certain tedious tasks that we can automate very quickly. Or, more importantly, look at the patient. How are all this care that is being given to this patient, how is affecting their quality of life? How much painful a biopsy can be. Those are things that you can see when you go in the biopsy room, which I actually do quite often, working with our urologists. So understand the data, how it is collected, and what are its limitations. So if you are in a space where these things sound a little bit far, find a clinicians. They're very excited about having their workload being reduced. So if you can automate stuff, they will be willing to talk to us. So find the experts that will be your users and shadow them and give them your tools. See what they think about them. Have them as being your first reviewer of your approach and then later on your paper. All right, so going back to, okay, we figure out why we want to do this. Let's go and talk about how we go about doing what we want to do. So the first part, we want to be able to label images. Of course, we want to identify aggressive versus indolent cancers. How do we go about doing that? Well, there is only one way I can think of, and that is doing registration between radiology and pathology. So specifically, I was thinking about Mr. Smith. Mr. Smith get this radical prostatectomy that will provide this beautiful sample that shows the entire prostate. Now I can get a very patient pathologist, and thank you for all the pathologists that sit down and annotate our data. I can get them to sit down and give us outline for where the aggressive and indolent cancer is located. And then what I do is, okay, we can get this information. We can actually register radiology and pathology images, applying the registration approaches that we have been talking about, and now we can label the data. The good thing about the space of pathology is that I don't need to always rely on pathologists to annotate this data. These whole mount images are ginormous, easily anywhere between 80,000 to 100,000 pixels by 100,000 pixels. No pathologist is excited about the idea of annotating that, but thank God there are a lot of AI approaches in pathology. Keep on working on those, please, because I want to be able to use them. And the idea is that, of course, we can get the pathologist, and I usually like to refer to the pathologist as human pathologist, and we can ask them to do clinically significant or indolent. They can provide additional information like extraprostatic extension. This is cancer going outside the prostate boundary. That's a bad indicator of outcome. But more importantly, I can take this data and I can actually push it into an AI approach that will give me Gleason grades. And that's what we actually did. We have AI approaches that do the Gleason grading, and we get this question very often: how well do they work relative to the pathologist? We did that study. I'm not going to go into the details of that. Short story, it's pretty accurate. And also the more important part is that you have to keep in mind that the reason why I want this, to use these algorithms, is not because I want the smallest part of these tumors to be visible. I'm going to project them back onto the MRI, and then the resolution of the MRI, it's very, very different than the resolution of the pathology. So of course I want a very good pathology system, but it doesn't need to be perfect. And because ultimately I'll take the said 80,000 by 80,000 pixels, and I'm going to project them in 200 by 200 pixels. That is the area in a prostate MRI that covers the organ that I'm interested in. So that's why, okay, it has to be good, but I'm not gonna fuss a bit if they don't find every single gland that has cancer in those images, because I'm not gonna see that on MRI anyway. So going back, I'm mentioned that I want to use the labels from pathology because they are ultimately the ground truth for cancer. And then we look very carefully at what our colleagues from the radiology side are providing in terms of labels. This is a label provided by a radiologist. We can see it captures that dark region in the T2 weighted image of the prostate, very good. However, when we look at the pathology, we start noticing a number of things. The number of things that we're noticing is that there are more than one lesion. There are actually 2 lesions, so the radiologist missed a lesion. Second of all, we also notice that there is quite a big difference between what we see, what the radiologist considers to be a cancer and what the pathology really shows as cancer. And we know that actually the MRI estimates the size of the tumor, but also because radiologists really want to get the things that they are confident that there is cancer, and they will outline just the part that is really truly considered to be clinically significant cancer. Now, when I look at this and then I look at pathology data, then I want to take all of these labels into account because I really want to find all the cancers, not only the ones that the radiologist has found. And so ultimately, the part that you train with, the labels that you train with, will affect the ability of your models to find cancer. And we spent quite a little bit of time thinking about that, and we even have a paper where we compare what happens if you train with radiologist labels, with pathologist labels, with all these very granular labels. So I'll point you to that to look at those details. But then it brings us to the second lesson that I learned looking at this, because we're talking about labels. Question the quality of your labels. How are these labels obtained? Who made them? What is really ground truth? Because I did mention that ultimately I like to think about pathology being the ground truth of cancer. You ask the pathologist in the room, they will tell you Gleason grade has a huge variability in terms of how pathologists assess Gleason grade. And then we should probably look at genomic. And it's a hard question. I think it's important to kind of think about them and actually test what does really make sense. Because ultimately, remember, we want to go back to that patient, got that needle towards the aggressive cancer, and some of these details may matter and some of them may not, but you have to be aware of the limitations to be able to do that. So I did mention that a big part of the things that we are doing is that we are aligning radiology with pathology images because we want these labels. But that, in the big scheme of things, is easier said than done. Pathology data is complicated. Actually, radiology data is complicated too. But if we look at this, this is the data from the same patient. This is the T2 weighted of a image of a prostate. We can see we have the 5 images going from the apex towards the base of the prostate. And now we look at the pathology whole mount slides for that patient. So we can see a lot of things. But the part that we're starting to see is it looks that is a little rotated. That's because where the data is mounted on the glass slide, it actually floats in a bath of water, and it actually does really rotate. The other thing that you notice is, and you can say, okay, fine, I'll flip my data, I'll do what the pathologists do, I'll align them mentally and all that kind of stuff. If you actually align them, you're going to notice that the cancer will move from the left side to the right side. Oh, that's another problem, actually. The way the data is scanned can be flipped. It's the same cancer, it stays always on the same side, but practically speaking, when I look at this data and I think about registering to create labels for ground truth, well, I have to deal with all of this. Well, we deal with that when we started. We, of course, deal with it manually. We said, okay, let's not deal with it. And then we'll go from there. And then in the next version of the study, we are like, okay, we do need to deal with this. So we recently created an end-to-end approach that deals with every single step in this process. And so we take the images as they are created, we segment the prostate in the pathology, we figure out how we should rotate them. These are AI models that have been trained to really figure out if we can flip the data, if we should flip the data, and then also how should we actually rotate this data so that it's aligned with what we know should look like in terms of left and right and top and bottom and all of those anatomic locations. So that gives us a nice representation of the pathology. We do the same with the MRI. We segment the prostate because we want that. But if you remember from my previous slide, I was showing 5 images of the T2 and then 4 images of the pathology. Well, they're not really matching one-to-one, or at least we have to figure out how they should match. So we have an approach that actually also focuses on how we need to stack these images relative to the MRI to actually have a slice-to-slice correspondence. And then ultimately, once I have that, finally, I can get to the registration part. Every single step here that is mentioned, it's automated, and they all have an ability to identify this different elements that we need in order to register them, but also they allow very easy human editing, because it's not always trivial to find some of these things directly from the data. So here is an example how we do the slice correspondence. This is another view of the prostate. So we see now a section through the prostate, not the axial anymore. I believe this is the coronal view. And then we see the pathology also in the coronal view. So we're trying to figure out how should I move this model relative to the coronal view in order to be able to fit it relative to the images. Now, we have been having quite a little bit of fun in identifying what's the best way to do this. And back when we actually started this study, and it took a little bit for it to be completed and published, we started actually with pics-to-pics in order to transform the pathology into a radiology image, and vice versa, a radiology image into a pathology image. And this is how we convert our data between the two formats, so we can actually easily, or easier, find correspondences between our slices. And you can see here a representation of how the multimodal approach does it. So we can get the H&E image and then convert it into an MRI kind of representation. And then it's a lot easier to actually identify which slice into the MRI actually looks like this. And also, like, one of the advantages of doing it in this fashion is that we didn't really care that the representation is perfectly accurate. It needed to be accurate enough, again, to allow the registration and finding slice correspondences. So I don't necessarily, I mean, I would love to create a representation or a version of the pathology that a radiologist would say, absolutely, this is how this prostate looks on MRI. But it doesn't really need to, because I really use it as an intermediate to the next step, which is the registration. And this summarizes actually our registration pipeline. It's very basic. I'm not going through the layer of the network, but it is a regression model. You extract features. You're going to figure out how to align the two images. You need affine deformation, and you need deformable, because you can't just center the images. You need to know exactly where they go. And we have trained these models with a number of data sets. We actually train it with our data from Stanford, which is cohort number 1, and then tested directly on other data sets. And there are a couple of public data sets, and now with the Chimera Challenge being also public, there is a third data set, but this is a little bit older. But both of these data sets, cohort 2 and 3, are actually public data sets from the Cancer Imaging Archive. They have very different characteristics, both in terms of the MRI acquisition as well as the pathology acquisition. For instance, this pathology is actually one of those stitched pathology images where they don't have whole mounts, so they take the quadrants and they kind of stitch them together. So that's a different kind of pathology to a certain extent. It's pseudo whole mounts. And then in the bottom, this is a data set where the pathology was actually scanned with a very basic camera, like really not a scanner, but really taking a picture of the glass slide. But for the purpose of, I want to get the labels from the pathology onto the MRI, that low resolution, as long as I have at least a human outline of it, it's good enough to do the registration and actually get these labels. Now, one of the things that we have done, of course, we compare how this approaches the registration using deep learning methods, compares to the iterative approaches. Rhapsody is the iterative approach that is actually also available in 3D Slicer, so you can use it right now. It has a nice example. What we are noticing is actually there is not much difference in how well things align when you compare a model that comes from an iterative approach compared to one that is doing it with deep learning. So that was a good thing. But the part that was actually interesting is that it's a lot faster. So deep learning based registration make the process of registering data a lot faster. But also because we have this entire pipeline that allows us to automate the different substeps, then there are a lot of things there that have been improved beyond just doing it manually. But as I did mention, one of the things that I did mention is that I don't always work on prostate. I actually want to apply these ideas and these principles on other organs, and one of them is breast cancer. And in breast cancer is very interesting. There are really not that concept of whole mounts where you take the entire sample and put it on a glass slide, mostly because the sample, the tissue is very large, and also quite floppy, so I think it's hard to put it. So they chop it. They essentially make little pieces out of this pathology slices. And one question that we wanted to figure out is, can we figure out how to put together these different pathology slices so we can recreate the whole mount, again, a pseudo whole mount by creating a pseudo whole mount. But how can we go ahead and actually put these things together using information that we currently have? So the radiology information that we currently have in the breast, which is actually a very interesting thing. It's called a faxitron radiograph. It's actually an X-ray of the tissue once it was removed. So they take the tissue out, they fix it, they slice it in the pathology labs, they put the slices under an X-ray, and they use this X-ray image to figure out which parts of this sample, which parts of this tissue to be submitted to histopathology. Because it's actually, when you have a breast tissue, especially in mastectomy, it's a lot of tissue. And if you push this all in pathology, well, somebody has to read them. And we can easily have 60 of this whole amount, like all these images that a pathologist has to go through. I'm sure they're all super excited to look at 60 images to make the case whether there is cancer or not. So, so they use this X-ray to guide at least the bigger region. So they want to know, okay, are there calcification? Should they have an idea where things are? So needless to say that we spend the time to figure out how to put this histopathology images, these little pieces, back together into the X-ray of the tissue. And now we're dealing with this from a perspective of, I'm still registering radiology and pathology data, but I'm solving it really as a puzzling problem. I have multiple pieces that they need to come together. I kind of know how they should look like at the end, because I do have an X-ray of the tissue before it was sectioned. And then we can actually apply, we have done this quite recently, and we have used a VIT that is trained with, we are simulating. I love actually registration methods that are using deep learning, because you can simulate what happens to the tissue, and we're training it in a single modality setting, but applying it in a multimodality. So in other words, we cut these pieces together, we're trying to figure out how to put them together, but we did that in a monomodal fashion, a training, but multimodal at inference. It works very, very nicely, and you can actually see some of the things that we wanted to kind of achieve with this is that we want to have this nice stitching boundaries between these images, but also that they need to nicely fit the yellow outline which comes from the X-ray of the tissue. And we can see how we have done that in this particular slice, but then here it's the actual entire sample. So you can see how nicely they come together. It almost doesn't even look like it's stitched. So it's really nice. And one of the ideas is that one day we'll end up having this register back to the MRI, which is kind of the goal. For now, we are only looking at X-ray, ex vivo X-ray, so X-ray taken of the tissue outside the body. So lesson number 3. We saw a number of things here. We improved the speed on some of the registration, but more important, it is to improve the performance of these methods, not only the speed, we kind of know that, but added functionality is even better. One of the things that we have, I really love registration done with deep learning as opposed to iterative approaches. And you probably can tell that I've done a lot of registration with iterative approaches over the years, is that I love the fact that we can simulate a lot of things that otherwise wouldn't be possible with the iterative approach, just because of the limitation of the method. So added functionality is even better. So let's look at the functionality that we ultimately added with doing this. So one note, I'm not the first person to do registration between radiology and pathology in the prostate. I'm probably one of the many people doing this over the years. But one of the things that we have done different, at least compared to many of the studies studies before us, we have actually, because we automated many of these approaches, we have been able to process a lot of cases. So right now, our cohort of patients with radical prostatectomy is about 250. Doesn't sound like a lot, but each one of these patients has about, in average, about 7 slices. So we have a cohort of about 250 cases with 7 histopathology whole month slides already registered. And with that, now we can go to the next step, which not a lot of people have managed to go, and really start training these models with Gleason patterns that we get from the whole mounts. And we have done that. We actually train a model with those Gleason patterns. But more importantly, we start realizing that we have this very unique data set. We have really pixel-to-pixel correlations between radiology and pathology. That's not very common. So we thought about, can we actually take advantage of the fact that I know exactly which part of my pathology image corresponds with which part of my radiology image. And what we have done is to think about how should we extract these MRI features, how to create MR signatures of aggressive and indolent cancer, given that I actually have features already in the pathology space, and then how do I do that, and how do I use them? So let me go a little bit more in detail there. So the idea is that I want to extract features from the MRI. I want to improve the difference between, okay, going maybe even one step further. I want to improve the difference between aggressive and indolent cancer, right? I want these algorithms to be able to find and distinguish better aggressive and indolent cancer. So in order to do that, I can actually guide the deep learning process towards extracting features that make them more different. And what we have done is to use this approach that we refer to as correlated feature learning. And as you all work with foundation models and all that, you can imagine very easily how I can extract features from MRI. I mean, it could be a foundation model. It could be, when we did this, which is a little bit ago, it was just VGG features. Foundation models were not around yet. So we have done that where we extracted features from T2-weighted images, any deep learning features, and then we did the same with ADC, and then we concatenate them. But I mentioned that I have the pathology image, and then the pathology image actually also I can create features from the pathology image. I can look at them at the high resolution, but I can do it at low resolution, and I can create features, really foundation-like features, foundation models-like features, from the pathology data, and then I can look what features in the MRI should I select. How should I combine them so that they actually correlate with features that I extract from pathology that are also linearly combined? So that's what this correlated feature learning does. It identifies which features and how do I combine them on MRI so that they look like features combined from pathology, but also because we don't want to just create spurious features. We want to make sure that the features that we select still reconstruct the data in the feature space. So we still have a good representation of the data once we use these features. So giving you a little bit more details there, this is an example of a VGG feature extracted from the T2-weighted image. This is going into the black box. Extracting the feature is obviously just an edge detector, ultimately, with different flavors. Do we see the same thing on ADC? We see the features here. And this is what we refer to as MRI biomarkers of cancer. This is a combination of these features. And it still kind of doesn't look like an MRI image anymore, but it doesn't need to. But more importantly, this particular biomarker, MRI biomarker, correlates better with this version of the data, which is a linear combination of pathology features. And that essentially, and then we can look, we have a variety of this correlated features that actually capture better cancer and the differences between aggressive and indolent. And of course, we can play with this process as we want to create these features and this MRI biomarkers that are better at distinguishing aggressive and indolent. So, and then if we have them, we know how to create these MRI biomarkers, now we can put them into a deep learning model and train with them. As we are looking into this, one thing that you're going to notice is that the pathology is not an input. We want to figure out how to still predict cancer on MRI, but without the pathology. If I make the pathology an input, then I cannot use it before surgery. I need the surgery to give me that image. So we really wanted to separate the steps in order to learn in the patients that I have the surgery, how do I create this MRI signatures, but then go back to just using the MRI version of the linear combination as input for our networks. And we have done just that, and we show how this approach, which we refer to our core signia, so correlated signatures for aggressive cancer, compares to other approaches, UNET and our previous version that is called SPCNet, which is actually based on an HED, which I believe Ron Summers has. I remember that we have been citing quite a little bit that paper because it's a study from his team. But more importantly, I think we have to look at how this results look like. So this is the T2-weighted image of a patient. This is the ADC, and we're looking through the patient going from the apex through the slides, and then we can see the different registration, the different images with the aggressive cancer in yellow, and then green, it's indolent cancer, and that's the ground truth. And you can see actually how our approaches are already starting to identify aggressive versus indolent within these patients. So lesson number 4, as you are developing these AI approaches, get outside your comfort zone. We all like to work in radiology, or we like to work in pathology. Do more, do both. It's hard. It's really hard, but it gives us such a unique opportunity to think, how do we improve patient care? Because I think that's ultimately what's very important, is like, how do we help that patient? So get outside your comfort zone in terms of data types, methods, right? We know we always, it's foundation models now, I guess I have to use foundation models, but yes, we are all going to have to use them because they're good. They do feature extractions very well, and why not use them? And then, of course, get outside your comfort zone in terms of what medical question you're going to answer or try to tackle, right? So in the process of developing these models, we have learned a lot about prostate cancer. One of the things we learned about prostate cancer, we knew that from our clinicians, but we know that prostate cancer is somehow heterogeneously distributed within the prostate. It's not everywhere. And we know about 70% of them are in the peripheral zone, and about 30% are in the transition zone. So we knew that from a clinical perspective, but we actually have data now. We have a ton of patients, and we know exactly where their cancers are. We know they're confirmed by biopsy. So we can go a little bit beyond that and not only say it's 30% in the peripheral zone of the prostate, but actually I can know exactly where in the prostate cancer, in the peripheral zone are located. And these are actually the representations that you are seeing here. The peripheral zone is actually the lower side of the prostate. You can see a kind of 2 nuclei or 2 regions where cancer is more often located. And then this is actually in the transition zone, and then you see another part that is very interesting there. And we can clearly see spatially is really not distributed in the same way. But why am I bringing this up? I'm bringing this up because we wanted to use this information in our models. We figure, okay, if I know that this cancer have to be more likely to happen in this location of the prostate, can I use this information to guide my models to look in that area? And what models would better work with this idea? Because it's a spatial distribution, and if it's not obvious, what model I'm going to is diffusion models. Diffusion models are learning kind of, we can guide them, right? You start from noise and you want to actually create something. You can start from noise and segment the tumor, so you can train them to do that process of segmenting the tumor. But in the process of doing that, how about we actually get this prior? So really use the spatial distribution as a prior, like we think in the Bayes sense of where should these models look like. So the diffusion model, the stable diffusion models are conditioned by the T2-weighted images. Of course, we want to have the images as an input, and then we use the atlas as another condition to really guide that denoising or renoising process in a way that actually allows us to go from the noisy image to the cancer in a better approach. And Cynthia Lee, which is a PhD candidate in my team, has done a great job at modifying the process of diffusion in order to account for this information. And we can show that if we actually guide these approaches using the spatial distribution of cancer, it actually allows us to better find cancer in these patients and improves AUC and improves specificity and Dice coefficient. But of course, more important, we actually did, of course, look at foundation models, and we have trained what we call as a foundation model of the prostate, where we really start with dyno features and then figure out how to combine it in order to really do prostate cancer detection in multiparametric MRI. And we can see here kind of the network and the ideas. And the good thing about this one is that it's really trained on a single sequence, but then we combine them together. The advantage of that is that we can actually deal with the fact that sometimes the sequences can be misaligned, and there are many problems that exist in this data. So this splitting kind of across the sequences actually helps quite a little bit, and interestingly enough, they generalize very well. So in our study, we tested them in a number of external cohorts through our collaborations, and we are noticing that they're generalizing very well. So lesson number 5. Keep up with new approaches, but don't forget to test the old ones. And one of the old ones, the one that comes to my mind, of course, is, this NN units. I love them, but I hate them, but I love them. They're really so good, and you should actually train an NN unit before you try to train any kind of segmentation model. And not only a vanilla NN unit, you do have to play a little bit with those parameters to get all the information and all the juice out of it, and then start doing your model. It creates a nice baseline that actually will help you develop better AI going forward. Very often we do it the other way around. We're like, oh, a good foundation model, let's try it. And then you do you spend the time, get it to work, blah, 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 and then you get to the NN unit, you're like, oh, it doesn't work as good as I was hoping in my mind when I was developing this. So anyway, keep up with your approaches, but also don't forget to test the old ones. All right, so going into, I want to be realistic about the time. I want to have a lot of time for questions. But as I mentioned, I spent a lot of time talking about MRI, and I show you Mr. Smith's kind of going through the process. So we detect cancer on MRI. We can do it better than before. But ultimately, let's go to the next step in this pipeline. This MRI is used to guide the biopsy, and in order to guide the biopsy, it gets fused with the ultrasound. The fusion is actually not perfect, and the fusion can create certain problems. For instance, we know clinically that about in 20% of cases, the cancer is upgraded between a biopsy and a surgery. And many people like to this is a problem that doesn't only come in the space of prostate. Actually, it's common in breast as well. And then very often people refer to this difference as a sampling bias. They didn't sample the right regions. That's why when we look at biopsy, we see more lower grade disease, and when we look at surgery, we see higher grade disease. So sampling bias actually, in my mind, converts in, okay, probably is misregistered. Something got misregistered because that MRI is supposed to be better, and because that information is there. And then second of all, we do know that the biopsy needle, like really the needle and how accurate a urologist can insert that needle, actually has errors as well. Well, we can't deal with that, at least not yet, but we can deal with the previous part of it, which is the registration error. We can deal and improve the registration there. But one of the things that we have been thinking about is, okay, these models that do registration have the same kind of architecture as the models that do detections. They extract features, but then they put them in some sort of a regression part that will regress the parameters of the registration. But we kind of figure out that these processes are not independent. We should be able to both register the ultrasound and MRI and actually use them to detect cancer on MRI and ultrasound. The ultrasound is the image that we want to use. That's the one that actually guides the procedure, but I have the MRI. So why not actually do this in a one step that allows us to really align the data, but actually more important, find cancer. We don't care about aligning the data. We really want to find where cancer is on ultrasound. So that's because that's where it's going to guide the biopsy. So we have done that. We have developed this kind of a little bit intricate network that will allow us to both do the registration and segmentation of cancer in the end-to-end fashion. This is a study that was just submitted actually this week, in which we are looking at how well we can align the prostates, but more importantly, how well can we detect cancer. And we can see here, of course, doing it in an end-to-end fashion is it is better. And we can see some visuals here on how the alignment works, how the ultrasound alignment works, and then as the data goes through different steps during the training, we can see how it gets actually better aligned, and then we can find cancer. Of course, this is just during the training, because at inference you just get the registered and the cancer detection in one step. So you're making that process faster. All right, and going to the last step of my presentation, I want to talk to you about, again, going back to the biopsy procedure. Ultrasound is the image modality that guides the procedure, but we're not using it. Like literally, the urologists kind of figure out where the prostate is located, but never really look for cancer. But as we are looking for this, we kind of figure out that in United States, Europe, it's a different scenario, but in the United States, not every man gets an MRI before their biopsy. Actually, only 36% of men get an MRI before their biopsy, which means 64% do not get an MRI before their biopsy. And that means their biopsy is only guided by ultrasound. But I just said you can't see cancer on ultrasound. They don't think that you can see cancer on ultrasound. So what happens if you drop the MRI from this pipeline? Well, clinical trial, like PROMISE is one of them, says that the sensitivity on ultrasound-guided biopsy is 48%. That means 52% of men will go home thinking they don't have cancer, but they actually do have cancer. We look in our data, it's a little bit better than 48%, it's 71%, but we still want to be able to say, can we actually detect cancer on ultrasound? Can we go to the step? Radiologists and urologists will tell you there is not information in the ultrasound to detect cancer. As I said, I like a challenge. As such, we have developed approaches. We started small. We said, okay, can we actually segment the prostate? And more importantly, can we segment the cancer on the ultrasound image? And we started with an NN unit in this context, but we trained this NN unit actually in a lot of data, because we really wanted to make the point, is there information in this ultrasound to actually detect cancer, and address all the nagging voices, aka our reviewers, complaining of the fact that we don't think there is enough information in this ultrasound images. And the short answer is there is information in the ultrasound images, information that AI can find, and actually when we look at the predictions, they can be quite good. They can definitely allow us to find some of these cancers, and we can see here the ground truth is in yellow, and then the predictions of the model are in cyan. So we can see here, we detect nicely the cancer there. We also have some false positives like this one, and so we do need to be aware of the fact that there will still be some false positives. But we also ask radiologists and urologists, can you actually look at this ultrasound images, and can you find cancer? And so I'm showing this an example of a case going through the lesion. Again, the ground truth is in yellow, which is we see here very, very nicely. And then the AI approach did find the clinically significant cancer, which is great. It's not perfectly overlapped, but I always think about this idea that when it comes to detecting cancer, yes, we like to define all the cancer region, but more importantly, I want to find a part that if I do target, I actually find cancer. It doesn't need to be, again, perfect. It just needs to be good enough to use it for targeting. So, so the AI approach was very good, and we look at the humans. By the way, the humans are the different colors that we see here, kind of yellow, green. We see a number of outlines on these images. And as you can see, they're really all over the place. They really were having a hard time finding that cancer. Only one person out of 8 has found the actual cancer. Everybody else has outlined all kind of other things. So yes, humans are not able to interpret the ultrasound images, but AI can, and maybe not perfect. There are still some false positives. This is an example, but we do also find the cancer, and I think that's the more important part. So we can answer the question, is there information in the ultrasound that can be used to find the cancer? Yes, there is. And more importantly, I am really an AI person, and as such, I really don't know yet enough about the acquisition process of an ultrasound. There is a lot of raw data that is acquired with ultrasound. RF data being very important in this context. This is the raw data before we see the B-mode image, which is really what the clinicians look at the screen. It's a very complicated data set. It's not very much available. So yes, I do think that using raw data will probably improve this prediction, but give it to us in 3,000 patients, because very often the raw data is not stored, so it's not really available. So very often we do have just the B-mode data. But the B-mode data, there are studies comparing a little bit the benefit of adding RF data to B-mode in detecting disease, and it helps a little bit, like 3-4%. But it's, again, I think the B-mode data actually is quite useful for this purpose. So anyway, so short story, this graph actually summarizes how well we can separate or how well the AI approach works compared to the humans. You can see here the sensitivity of the humans. So in the studies, we have people that had a sensitivity going anywhere from 11 to 77. So some humans are better at finding these cancers as others. Obviously, many of them were more going on the side of caution, not outlining things. So the specificity of the human is very good. So we have a little bit more false positives. But more importantly, we went to the question, okay, what is the added value of this AI approach, right? Is it, as I mentioned, the ultrasound-only guided biopsy, which is a systematically sampling the prostate, already finds some cancers. We see that the number of cancers that this systematic procedure found is about 70, almost 72% of cancers. So if the systematic procedure finds 72% of cancer, how much does a MRI interpretation or a radiologist interpretation of MRI adds? Well, we look at that and we said, okay, they found another 22% of cancers that we didn't see with the systematic biopsy. Well, our approach using AI targeting in those same give us exactly the same. That starts with 72 because we can already find those 72% of cancer. But if we would target the lesions that we find by AI, we find exactly the same number of cancers. Not the same cancers, by the way. There is a little bit of a shift there. There are some cancer that ultrasound AI finds that the radiologist didn't. But ultimately they're comparable, and then we did test this in the biopsy cohort as well. The biopsy cohort doesn't have a very good ground truth because we kind of always compare it with the radiologist. We don't know exactly the real where cancer is located, so we kind of extrapolated certain things, but we still see that the trend is the same. The AI approach on ultrasound is actually could help detect the cancer. So lesson number 6. Focus on the value added to the patient. And then in this process of thinking about it, think about the 1% increase that you might get in your AUC or DICE coefficient, if that actually down the line translates into any benefit for a patient. Just do that exercise. It is a hard one, but is one that is actually quite important. So I'll stop here, just summarizing, saying that we have made many contributions on how to register radiology and pathology. We continue thinking about that quite a lot. We made a lot of contributions on how to detect cancer on MRI. More importantly, now we are looking at ultrasound as a modality that is a lot more available and easy to acquire. And then we're making progress there as well, being able to find cancer. Lesson number 7, tackle hard problems. Reviewers are not always kind. Keep on pushing. It's not about the reviewers. It's about the patient. So keep on pushing. It's not make the good science. Provide the good arguments for the clinicians to actually be interested in using your approaches. Make sure your data, like your statisticians, agree with you as well. And then more importantly, think ultimately about the benefit to the patient. So with that, I'll stop here. I'll say that this approaches, we're looking really at assisting radiologists and urologists in their interpretation of the images. We want to help them guide these procedures. And of course, we want to put them in the hands of the clinicians. We want to be able to have methods that work on all kind of MRIs, all kind of ultrasounds. It's the world. There are many problems that we need to still solve. And maybe my final lesson, with power comes responsibility. You have very unique skills, use them wisely, use them to do good, think about our patients, and think about you being a patient or your dear ones being a patient. Go in those shadow clinicians is very important. So anyway, stopping here. This is my team, my collaborators, and these are our funding agencies helping fund some of this research. And of course, please, I look forward to talk more with you. I love this conference. I talked quite a little bit with a lot of people. We're hiring, so if you are a postdoc looking for opportunities, please join my team. But I'm looking forward to your questions.
So we have time for a few questions.
Hi, thank you for the very interesting keynote. Maybe a clarification on how you obtain the ground truth of cancer on the ultrasound. Maybe I missed it, but you said
yes, I didn't talk too much about it. Very good question. Question the labels. They are actually coming from registration between MRI and ultrasound. Okay. So at Stanford, every patient has an MRI before their ultrasound. And because of that, we actually the data is registered, we have the registration and all that kind of stuff, but we also know if that lesion that was targeted, whether it had cancer or not, and what grade of cancer. So it does come already from the registration of MRI and ultrasound that is used clinically. So not a perfect label, good catch.
Okay, thank you very much.
Question the labels.
Hey, great talk, thank you. Regarding the last example with the ultrasound to MRI again, do you use the 3D information from the ultrasound? Do you use, do you reconstruct the 3D from the sweep, or is that not useful?
Yes, good question. We do. The vendor that we use actually reconstructs the ultrasound from the sweep. They have a robotic arm that does that specific, that's part of their kind of fusion system. So because they provide a fusion system, they need to reconstruct the ultrasound in 3D that they are going to use to actually be able to match the MRI to the ultrasound, and they have a system to go back into the 2D sweep. So they track the probe and all that kind of stuff to be able to do that. So again, it is it's as good as it gets in terms of we already have a reconstructed data. We don't have to deal with the reconstruction part. And it actually gets us to the question, is there signal? Like, as I think the big problem that I've been trying to address for a little bit now is answering the question, is there signal in ultrasound to detect cancer? So yeah, with that data, I think but the data is in 3D and the registration, everything happens in 3D, which is also, yeah.
Cool, thank you.
Thank you.
Yeah, thanks. This was really great. I just have a quick question. So there are some cancers that are not visible on MRI. And so are these visible on ultrasound? So that is one question. And then the other question, just a brief question is, if I understood this correctly, so the ultrasound is really used to tell whether or not there's cancer. But how about, is there any information about the grade or the severity of the cancer?
Yeah, all very, very good questions. MRI invisible question. I've been thinking quite a little bit about the MRI invisible lesions. Of course, if we do registration between whole mounts and MRI, we actually get the MRI invisible lesions. They're still very hard. They're called MRI invisible for a reason, because they're not easily visible. I actually like to categorize them in MRI invisible, like truly invisible, even once you have the pathology. There is the other category that I call hardly visible, which means if you see the pathology, you can say, well, I can kind of see something on MRIs. Maybe there was a signal, but maybe it's not strong enough to see it when you don't have this information. I've been talking recently with other folks that look at MRI invisible, and specifically Thomas Myrti from Helsinki. And one of the reasons why there is a belief that the reason why a lesion, a cancer, is MRI invisible is the same reason why it's not clinically relevant. It really doesn't have the markers of bad cancer that will end up killing the patients. I think that has been one thought. We do know that clinicians really want, we get very often the question, hey, are you going to do overdiagnosis by finding these lower grade cancers and all of that? So I think there is a lot of debate in the field whether finding a less aggressive cancer should be done, right? You overdiagnosis or not. So I think clinicians really want those clinically significant. They really want the patient, they want to find a cancer that will kill the patient. I think shortly said, like, and then, yeah, so I think we can debate this question, then we can go ahead. I can probably talk for a while. The other question about, can I see this on ultrasound? Probably not. Okay. I mean, ultimately, I think we are trying to go for clinically significant cancer. Again, hopefully going for those the cancers that really kill the patients. But yeah, so I personally, coming from an AI perspective now, I would love to find all of these cancers. I understand that clinicians don't want to see the indolent cancers or cancers that are not visible. But if we do a good job and find them and tell clinicians that they are there but indolent, then they can make a decision with that, which I think it's an informed decision versus I don't want to find them. I don't want to find them. So, good.
Okay, so thanks, Mirabella, for like the great talk, and yeah, enjoy your lunch, guys.
All right, thank you all.
Our afternoon oral session of the third day of MIDL. I really appreciate everyone coming. My name is Bennett Lamb, and I'm from Vanderbilt University.
I'm Marco Castellaro from University of Padua in Italy.
And it's our pleasure to host this session. I'm going to go second because I like even numbers. So Marco?
So, since I like odds. So the first talk is neural fields for tissue attenuation curve reconstruction in sparsely sampled time-resolved CT. I come here at the stage Lucas De Vries. Please go on. Yeah, yeah.
All right, I'm really excited to be here today to present our work on neural fields for tissue attenuation curve reconstruction in sparsely sampled time-resolved CT. And this time-resolved CT imaging is important for the diagnosis of acute ischemic stroke. So by tracing a contrast agent through the brain, we can determine which part of the brain is still salvageable, which part is already diseased due to the reduced oxygen supply. But we can also use it to find, for example, the occlusion location or assess the amount of collateral circulation. So the standard way to do this is to use CT perfusion imaging. And CT perfusion imaging captures a series of CT images after the administration of such a contrast agent. These images are then transformed into a series of perfusion maps. And these perfusion maps depict information about the blood flow, the transit time, or the delay of blood, for example, in the brain. However, we need around 30 acquisitions to get these perfusion maps. And each of these CT acquisitions imposes radiation exposure to the patient. And moreover, since this scan takes about a minute or so to complete, patient movement can induce motion artifacts in these CT images, which can harm this perfusion analysis. Now, as an alternative, some hospitals opt for multi-phase CT angiography. And together with baseline non-contrast CT, this allows for the interpretation of 4 different time points of this contrast arrival. Now, the main benefit is that there's less radiation. But the problem is that there's no straightforward way to get these perfusion maps that we like so much of CT perfusion. So, in summary, CT perfusion is limited due to the radiation exposure and the motion sensitivity, while multi-phase CT angiography is not the only answer, since there's no straightforward way to get these perfusion maps. So we propose one method to address these issues, both in CT perfusion and in multi-phase CT angiography. And we do so using neural fields. Now, a field in physics is nothing more than a scalar or a vector quantity defined over a particular domain. And you can think, for example, of the temperature field on Earth, for example. Now, a neural field is a neural representation of such a field. So it's a field which is parameterized by a neural network. And these neural fields are typically trained by using a norm-based loss function, using some observations on the domain and training this neural field, which is an MLP, as a function of the coordinates of the domain to represent these data. Now, you can imagine that if we want to learn various neural fields of a larger set of fields, of temperature fields on Earth, for example, it's quite inefficient to train a separate neural field for each of these fields. We would, for example, like to leverage some information about the geography on Earth, for example. Or we would, and also training thousands of neural fields, if you have thousands of fields in your data set, is just computationally really inefficient. So that's why we use something which is called a conditional neural field. And the main difference between a normal neural field and a conditional one is that we use an additional conditional variable as an input to the neural field. With this conditional variable, the network is able to describe the large variety of fields in your dataset. So we have one network with one set of network parameters. And we have a latent variable initialized for each of the fields in your dataset. And all of these things are learned during training. So we train and the network parameters, but we also learn these latent variables for all of your instances in the data set. Now at inference, we can do something which is quite neat. We can sample part of the domain, find the latent that best fits the data while keeping the network parameters fixed. And then we can use this latent to also make predictions on the rest of the domain that was not observed. So how does this then translate to CT imaging? Well, we can also view the distribution of Hounsfield units in a CT scan over the temporal, spatial, or maybe even spatial temporal domain as a field. And this is exactly what we're going to be doing. So we're using the temporal domain only in this case, and we're going to learn a neural field to represent the large variety of tissue attenuation curves that we come across in time-resolved CT imaging. So the method is called STAR, Sparse Temporal Attenuation Reconstruction, and it is trained using simulated phantom data. So we have simulated tissue attenuation curves, and we learn this neural field as a function of time and this latent variable to represent the large variety of this tissue attenuation data. And for all of these curves, we know the ground truth perfusion parameters. Now at inference, we can sample data from slightly different but still relatively similar domain. For example, CT perfusion curves from real CT perfusion data, or potentially even the time points and the Hounsfield units corresponding to locations in the brain from this multi-phase CT angiography data. We keep the network parameters fixed, only backpropagate through the latent, and then using that obtained latent, we can infer the full temporal domain. When we do this for all of the spatial locations in the brain, we end up with a reconstructed CT perfusion image, which we can process with off-the-shelf CT perfusion software. So we have various loss functions. We have a data loss, which is a norm-based loss function that we use to learn from the observations that we actually sample. We have a regularization loss, which keeps this latent space of these latent embeddings somewhat compact. But this latent space is not really structured. And since we train with simulated data, we also have access to the ground truth perfusion values. And this is exactly what we're going to be using in our contrastive loss. So we have a contrastive loss that steers the latent variables for curves corresponding to similar perfusion settings to also be close together in the latent space. So for any two curves, we compute how similar they are in the perfusion parameter space. If they are similar, we also pool the latents in the latent space somewhat closer together. If they're dissimilar, we push them a bit further apart. To summarize, we have a method which is trained with simulated phantom data. The network parameters that we obtain are used in the neural field, and we fix these network parameters. Then we make a new observation, only backpropagate through the latent, and then infer the full temporal domain. And then we run CT perfusion analysis software. So we do experiments with simulated phantom data, with real CT perfusion data, but also with this multi-phase CT angiography data. So for the phantom study, we have a lot of tissue attenuation curves simulated with more than 700 different combinations of these perfusion parameters. We fit STAR to a subsample of the time points. Then we infer the curves, run CT perfusion analysis software, and then compare the perfusion values that come out of this software. So here the reference is the full desampled CT perfusion data from this phantom. So a full 30 time points. The baseline is a gamma variate function, which typically very neatly describes the tissue attenuation curve, and we also fit this to the sampled observations. I mainly want to go into the scenario where we sample 4 out of 30 observations, and these time points also align with this protocol of multi-phase CT angiography. And in this case, we have strong agreement with the reference perfusion parameters and significantly outperform this gamma variate baseline. So for the CT perfusion study, we sample time points and Hounsfield units from real CT perfusion cases. Again, we fit STAR to the model, find the best fitting latent, infer the full temporal domain, and then run CT perfusion analysis software. So now we actually compare the volumetric agreement between the infarct core and the penumbra. And we do this with 2 commercially available software packages. So the reference data is here the fully sampled CT perfusion data, so all 30 time points. And the volumetric differences that we observe are actually within the range of typical inter-software variability that we observe. Also qualitatively, the perfusion maps that are generated from the fully sampled CT perfusion data look very similar to the perfusion maps that are generated from this star-derived CT perfusion imaging. So this is only generated from 4 out of 30 observations. And also this we show for both of the commercially available software packages. Lastly, for the multi-phase CT angiography study, we sample time points and the Hounsfield units from multi-phase CT angiography data. Again, we fit star to the observations. We find the best fitting latent and infer the full temporal extent. Now we do a qualitative evaluation and we compare to real CT perfusion scans. So here we have a paired data set of patients that underwent both CTP and multi-phase CT angiography. So this is typically never really done. So the hospitals typically use either CTP or multi-phase CT angiography. So this is quite a hard data set to obtain. So that's why we only have 5 patients to show these results. And we treat it more or less as a proof of concept study. But also using these multi-phase CT angiography time points, we are able to find the same hypoperfused regions, although the perfusion values are slightly different. So we enable this perfusion analysis from multi-phase CT angiography data. But since the perfusion parameters are slightly different, we do feel that we are not really that accurate enough for volume estimation. So to conclude, we presented STAR, which is a neural field for tissue attenuation curve reconstruction from 4 out of 30 observations, which is an 87% reduction. So this could enable significant radiation reduction, for example, but it could also help to correct these motion corrupted frames that we so often observe in our data. And all of this we can do while maintaining this diagnostic quality. We enable perfusion analysis from multi-phase CT angiography. So also hospitals that do not capture CTP can still get some perfusion maps out of their data. And because we focus on generating these tissue attenuation curves rather than the perfusion maps, we are compatible with any clinically available commercial software for CT perfusion. So I'm happy to take any questions now and hope to see all of you at the poster.
So any question from the audience? Maybe I have one to start.
Sure.
So your framework is actually doing and dealing with the reconstruction, right? So do you think that it can also be extended to an end-to-end quantification of the perfusion starting? So incorporating also the analysis that now is done with the software?
So in my work previously at MIDL, I worked on the perfusion analysis side of the story, also with using neural fields. And I think you can actually tie those things quite nicely together. And
you already tried that?
It was the intention to actually do this for this work, but at some point we ran out of time. So that's how it goes. Yeah.
Thank you. I have one extra question. Fantastic presentation of the neural fields and the description and how you got this all working. Have you done any comparisons with classic approaches like a ridge regression or a lasso relative to your dictionary? To the 735 basis sets that you have?
To the 7?
To the physics-based model that you created.
Yeah, but what, in terms of which comparison are you talking about?
A non-deep learning traditional sort of dictionary approach.
Yeah, so we did compare. So the problem with a lot of things is that you cannot do extrapolation for these tissue attenuation curves. And you can also, like the other methods that we tried, the deep learning methods that we came across all wanted at least an interval of 8 seconds, for example, and our first interval is already 16 seconds. And these methods could also not extrapolate, which we are kind of generated a shape model, right? And this shape is just transformed in a way to make it fit the data best, but it will always keep the shape that we expect of this tissue attenuation curve. And with the curve fitting, we saw that especially at the extrapolation part of it, it would just not really work nicely.
Thank you so much. That was perfect. We look forward to continuing the discussion at the poster session.
Thanks.
And up next, we have Thijs Kuipers talking about self-supervised synthetic cerebral vessel tree generation using semantic sign distance fields. Thank you so much.
Great, thank you so much for the introduction, and I'm really happy to be here to talk a bit about my work on creating synthetic patients for stroke research. So acute ischemic stroke occurs when a clot blocks the blood flow in a vessel in the brain. And the treatment that we currently have, like mechanical thrombectomy, which you can see here, when the outcome of the treatment really depends a lot on a variety of factors, like the location of the clot, but as well the anatomy of the vessels. And that's why stroke research is still very much working on improving these treatments. But developing new stroke treatments actually requires very expensive clinical trials. Oh, could you hear me?
Yeah.
Okay, perfect. Very expensive clinical trials that take a long time to perform and are quite risky. But now imagine that we could run these clinical trials virtually at a very large scale without any risk in a shorter amount of time. And that is the promise of in silico clinical trials. However, in order to do this, we need access to very large data sets of virtual stroke patients. And unfortunately, these don't exactly grow on trees. And that's where my work comes in, where we generate synthetic stroke patients. And actually, this is what we did last year, right here at MIDL. So we generated these small trees, and this method actually worked quite well. But then I was wondering, okay, what if we need to generate bigger trees? Will it still work? An example of such a tree is this one. This is the circle of Willis. And as you can see, it consists of many more vessels, more complex topology, looping structures. So we trained our model on these kinds of vessel trees. And well, as you can see, it didn't really work that well. The topology is completely incorrect. So yeah, not very useful. So I asked myself one simple question: can we do better? Now, to answer that question, we of course need to know what exactly went wrong with the previous model. So just as a quick overview, this is how it worked. It was a denoising diffusion model. So we started with noise, and it would generate a point cloud that would represent the vessel geometry as a sense line. And then we used a separate algorithm that would actually connect all the points and basically construct the tree topology. And then from there, we can create the meshes. But this reconstruction algorithm assumed that the point clouds were mostly equidistantly spaced, and this assumption does not really hold that well when the point clouds, the vessel trees, become more and more complex. So really, what we wanted to do, of course, we could say, okay, we can fix this reconstruction algorithm, but what I really want is something that can basically go directly to generating the full mesh that is ready to use for simulation without all these intermediary steps. So that's what we're going to do. So what do we need to do to generate shapes? Well, first, when we look at a shape, we can consider it as a function, an implicit shape, which basically is a function that takes in an input point and it outputs some scalar. And a particularly powerful one is the sign distance function, where we model for some input point the distance, the shortest distance to the surface of the shape, where we define the distance to be negative when we are inside the shape. And then the shape itself is represented by the zero level set. And of course, we just heard about neural fields or neural representations. We can represent these kinds of functions using neural networks. So it's a neural network, it takes in a coordinate and it spits out this distance, and then we can reconstruct the field and extract the mesh from there. And typically, these neural fields are optimized in a supervised setting with a pre-computed ground truth sign distance function. However, we don't always have access to a ground truth sign distance function because we need to know which points are inside the mesh or outside the mesh or outside the shape. But as you can see, for example, here, this is just a hollow tube, so there is not really any inside or outside. So yeah, we really want meshes to be watertight, but we don't always have access to those. Fortunately, we can actually let the model take care of this. Because STFs have a very neat property, they satisfy the iconal constraint, which simply means that the norm of the gradient of the STF function with respect to some input coordinate should be of unit length. And intuitively, that just means that if I move some distance away from the surface of the shape, then the STF function output will have increased by that distance, right? That kind of makes sense. And it turns out that just having this constraint and having our STF represent some surface actually is enough to fully define the entire STF for some shape. And we can write it down as a training objective like this. And the benefit of this is that we can learn this STF representation from any kind of surface representation, be it point clouds, meshes, voxel representation, it doesn't really matter. And we can go one step further because we also want to generate this tree, but it consists of multiple individual vessels, and we do need access to those vessels. So we can consider the STF not to just output a scalar, but actually output a vector, where each of these vector components are the different labels in our object. And we can optimize that using mean squared error, and then together we have some kind of joint semantic shape representation. Now, as my colleague just explained, these models can not only represent just a single shape, but we can condition them on a conditioning variable, some latent variable, and then we can have a single network that can represent many different shapes. And we get access to these latent variables simply by encoding semantic point clouds that represent our shapes to these shape latents. And we obtain a traditional encoder-decoder setup, and when we train that using variational inference, we actually already technically obtain a model that we can generate new shapes from. But when we actually try to generate new shapes from this model, we get something like this. So what's going on? Well, we assume that the distribution of shapes follows this nice unit Gaussian, but in reality it would look more like this. It's full of holes, and the reason for this is because we want to promote reconstruction quality of the shapes over learning this nicely distributed shape space. So how do we sample from this? Well, what we can do is use a denoising diffusion model in latent space that learns this mapping. It learns us to steer from this nice unit Gaussian distribution to this more complex shape distribution, and then we can sample from that, denoise it, and decode it, and we get something that actually reconstructs to a plausible shape. Okay, so that is basically what we did. So let's see, did we do better? And before we actually look at some results, we first need to define what does better mean. What are we actually looking for in our synthetic populations? So first, we want our synthetic population to be representative of the real population. Secondly, it should be diverse. We don't just want to generate the same handful of shapes over and over. And finally, we want our shapes to be novel. I mean, our model wouldn't be very useful if it was just producing copies from the training data. So we want to be right here. So let's see how we did. And also put them up here so we can keep track of them, and we tick off the boxes when we see we satisfy one of these criteria. So we start with generating some shapes from the TopCow data sets, which, by the way, I highly recommend checking out if you're interested in vessel segmentations. It's a really nice data set. So here are some examples of our previous methods, where we can see incorrect topology and just weird stuff going on. And then, oh, I pressed the wrong button. And here are some examples from the new method. And as a reference, here are some examples out of the real data sets. So we can immediately see that for the real data and the synthetic data of the new model match up. We also see that in the synthetic population, we kind of generate a different anatomical variation of the circle of Willis that you would see in real people. And overall, the topology is correct. We don't have any weirdness going on here. And of course, because we generate all these different components within this tree, we can actually analyze each individual vessel. And basically what we want to see here is that we have this distribution, for example, of the length of the vessel for the real data set, and then we want it to match up for the synthetic data. And we see that it is indeed the case, and we can measure different things, of course, and it all lines up. Also want to see, can we even generate more complex trees? This is from Vascucint, and we can do that. And this is actually an interesting data set because we can interpolate between a very simple tree and a very complex tree. And what we see is that this very tiny tree naturally grows into a more complex one. So this model actually really understands what makes a tree a tree. And then finally, of course, we need to see, are the trees novel? So we can simply just compare the synthetic trees, find the most similar tree from the real data set, and compare. So the real trees are here in gray, and we indeed see that the synthetic trees are different. So we are generating new structures. So we can also take off the novelty. So what are the main takeaways? Well, with self-supervised SDFs, we can learn a very nice, high quality and structured semantic shape representation for shape generation. And using latent diffusion, we can actually generate vessel trees that are quite representative, diverse, and unique. And I think, finally, we can answer our question, did we do better? And I think we did. Thank you very much.
We have time for 2 questions. Thank you.
Hi, thanks for the great talk. Can you go back to the slide 21?
Which slide?
21.
31.
Oh, sorry, 21.
31?
21.
21.
Yeah.
No, I don't have 31.
There is a comparison between the before, after, yeah, this one.
Okay.
So my question is, you can see the first and the second one. The first and the second generated image looks very similar to each other, and the third one and the last one also very similar. Third one, last one, and the one before last one also looks very similar to each other.
Mm-hmm.
So is there any reason? Because their ground truth doesn't similar to each other, right?
So you're asking why the trees are very similar to each other?
Yeah.
Well, this circle of Willis is kind of a structure that is a very well-defined geometry, so they're all kind of similar to each other. So yeah, that's what we also see in the real data and also then in the synthetic data, of course.
Oh yeah, so my point is for the real data, actually this, for example, the third one, fifth one, and the sixth one, actually they have just like variations, but after, during the synthesis, these variations is diminished. And
how do you mean? I don't think I actually understand what you're asking me.
Okay, maybe you can talk it later during the post session.
And this is a wonderful portion of MIDL that all of our orals get to have a poster, so we can all come and talk to you in private in a minute. So thank you so much for highlighting the benefit of MIDL. Thank you again.
Okay, so we go to the third one. So binary format, 1-bit self-attention for long-range transformers in medical image segmentation and 3D diffusion models. Yes, Eric.
This is the one, right?
Yeah. First one's missing. Can I go back to the first slide? It started on the second. It's the PDF. Okay. Yeah. Great. Thank you. All right. Thank you very much for the introduction. I'm Matthias from the University of Lübeck, and I'm happy to present my work on how we get transformers for medical image segmentation and 3D diffusion models to work on really long-range sequences. And to do this, we introduce 1-bit self-attention. So many of you know that vision transformers excel in capturing global context. And with that, they improve over CNNs that usually only see a small piece of the image. And in particular for segmentation, where we might not always want to have multiple scales, but really want to feed in like all the information from smaller patches into a vision transformer to do the segmentation. This can lead to problems where the larger sequence length leads to a poor scaling of the transformer. On the other hand, the effective receptive field is really great in the transformer, so let's see how we can fix this. First, have a look at the key components that make up a vision transformer. So starting from the token embeddings, where we have our patches, we go through the individual blocks that consist of the self-attention and the feed-forward network, or MLP. The MLP is quadratic in channel, but just linear in the number of tokens. And the MLP itself can be approximated using low rank or mixture of experts, as done in recent LLMs. So that's kind of covered. But the global self-attention is quadratic in sequence length. So if our image is quadratic in the number of patches compared to the image width, or in a volume even cubic, then this gets us to the power of 4 or 6 into the sequence length. So how can we improve efficiency without losing this great global context? There have been some prior works on efficient attention, for example, group query or multi-head latent attention that are used in Llama and DeepSeek. And there's always this way of doing flash attention, which is quite memory efficient, I/O implementation in CUDA kernels. And there's also been work on sparse attention, where we want to find more similar pairs of keys and queries using some efficient search techniques such as local sensitive hashing. But we tried up the different route in which we look more at the quantization of our values that are used to compute the self-attention scores. And we wanted to go quite drastic here and go to binarization. Ideally, if we would have binarized tensors for query and keys, we can use the Hamming distance to replace the matrix multiplication that makes up all this computational complexity. And we will later on see that a good approximation is having a binary vector combined with a single scalar float value to represent each of these keys and queries. This can lead to a 6 times or even more energy reduction compared to the floating points. And there has been some previous work called BitNet for LLMs or MetQ for CNNs that showed that these drastic quantization strategies actually lead to comparable performance. But so far, those approaches only have used binarization at inference time. So we still need to use float precision during training, and this is a limitation if we want to train really big 3D transformer models, because we then also want to use this efficiency in training. So here's our model, or our approach. If we are given some inputs that are mapped linearly with the trained weights to the query and the key tensors, we want to somehow obtain the self-attention matrix and then multiply it with the values to get our output, right? What we do differently here is that we split the query and key into 2 types, the binarized version
and a scalar weight. And if we have this, then we can compute, as I mentioned before, the self-attention as a Hamming distance between the binarized strings. We simply need to multiply it pointwise with our outer product of the scalar weightings. The problem still is that this binarization isn't differentiable, so this will lead to no gradient. But what we can do is we can derive a gradient based on these single scalar floating point weights. And I have two different versions of doing this, which I will explain on the next slide. If we have them, then we can rewrite the backward pass so that it also uses the Hamming weight instead of the matrix multiplication for the self-attention part, and then also has a smaller matrix multiplication plus a pointwise multiplication. So our efficiency gains stem from having the forward pass for the attention, not using any full precision matrix multiplications at all, replacing them with integer Hamming distances and a scalar multiply, and reducing the backward floating point max from n squared d to n squared just. And we can see in these bar plots that the amount of work that is spent on the self-attention, the dark green blocks, are actually almost negligible in our Hamming or binary transformer. So how do we get the scalar weight so that it's differentiable? We have two different options. Either we can use Bernoulli sampling to do this going from floating point to binary value, and then we just take two samples and combine them with the bilinear weight. Or we can add a small MLP that predicts the weights using the quantization distance from this binarization step. There's also a third option, which I will mention in the experiments later, that uses a so-called step-through estimator. This works also and doesn't need any specific technique, but this still requires the floating point precision for the backward pass, so it's not really efficient. So in our experiments, we leverage some pre-training from Dino VITs, and we use the model S8, which means they have a really small patch size of 8 by 8, so we have really a lot of tokens. Some parts of the model are trained from scratch. For example, the self-attention weights that we replaced with our binary self-attention. And some are used from the pre-training, for example, the patch embedding and the feed forwards in the earlier layer to really kind of make use of this the self-supervision. And as you can see, otherwise the segmentation architecture is really simple. We don't have any multiple resolutions, it's just a single scale. So here are some visual results. We use the cross-molar data set, a spine data set with vertebras and disc segmentation, and also AMOS, which is not shown on this slide, which is abdominal organs. And here we compare the most extreme versions, our proposed binary former on the right-hand side, where we can clearly see that there is really good coverage of the different vertebras and discs, whereas the most extreme version of binarization, which doesn't include any gradient, so just a stop gradient, which is also of course efficient, has some segmentation errors, and also in the cross-molar case we can see here a little bit of an over-segmentation on the wrong side. We can also quantify this, and we see that even using the step-through estimator I briefly mentioned, that still requires full precision for the backward pass, is 3 percentage points less good than dice coefficient, and compared to the stop gradient, we're about 7 percentage points better. The binary training is even on par or sometimes better than the full precision baseline on the average over all these data sets. So this is quite convincing. And we can see a theoretical speed up of about 30 times if we just consider the computations that we need in the scaled dot product attention. However, this is the small caveat. This would still require some customized CUDA kernels, which we weren't yet able to implement. We have some experiments on the public code on MPS kernels for Mac. There it works, but yeah, this is still work in progress. And we did some further experiments The first one is on pixel-wise transformers. This just means we're treating every pixel in a small image as a token, and this also generates these really long sequences. And it also enables us to compare to some of these previously mentioned sparse attention works. For example, learnable hashing, where we are 5 percentage points better, and reformer, where we are 10 percentage points better. We also did some experiments on the 3D diffusion model. For this, we trained a vector quantized diffusion model with unleashing transformers. And the task here was not to just generate images out of noise, but to do some kind of in-painting task where we have set these tokens in the middle to random and then ask the diffusion model to correct them. Here we actually see no significant numerical or visual differences between the different versions, which could also be attributed to the fact that the VQ transformer also has other elements such as a convolutional autoencoder. Yes, looks fine. So with this, I'd like to conclude. We have demonstrated that it is feasible to use just 1-bit attention if we can make it differentiable, and the computation can be done in this low precision in both forward and backward paths. This enables very long-range context for transformers, so it could have a positive impact on medical imaging. We could use smaller patches, we could use bigger images for 3D diffusion models if this is used. In future work, we still have to address the implementation issues of actually getting custom CUDA kernels for 1-bit operations. I think there are some techniques to go there. And it would also be nice to see how this can be combined with weight quantization. I only looked at the kind of like the attention score quantization, but the weights itself can also be quantized. If you're interested, there's a 3-year PhD in postdoc position available at my lab. Just email me, and there's also the code. Otherwise, I'm happy to take some questions now or later at the poster. Thank you.
Any question from the audience? So, yeah, I'll start with one. Thank you for the really impressive work that you have done, and thank you to take care of this efficiency that is always needed. I was wondering, what is your next step in using and extending this framework to other parts of the transformer?
Yeah, very good question, good point. One step I already mentioned, like having weight quantization would make sense. I think in the end, yeah, there's a lot of inefficiency in transformers. It's not just in the self-attention mechanism, it's also in the MLP, for example. But it's also sometimes difficult to, there's a discrepancy between how much can we improve the efficiency in training versus efficiency in inference. Sometimes it's just harder to train a model that has fewer parameters or lower precision, and then we might kind of hide away a little bit of the performance if we don't train it to this very perfect point that we could have reached with the higher precision and larger number of parameters. So it's a bit unanswered.
Maybe I have. Do you have?
Oh,
we can go on.
Do we have time for one more? No, I think we're on time.
Okay.
So thank you so much. Appreciate it. So up next, we have Aravind Krishnan talking about anatomy-guided multipath cycloGAN for lung CT kernel harmonization. Thank you very much.
So thank you for the introduction. Hi, everyone. Let's get started with the talk. So in low-dose lung cancer chest CT scans, we have reconstruction kernels which impact quantitative imaging. Now, the CT kernel here is a filter that's applied to the raw projection data that modifies the texture of the anatomy in the image. So here what I'm showing are two kernels from the Siemens scanners. One is B50F for the hard kernel, which is sharpening the texture of the anatomy here, but is amplifying the pixel noise. And then we have a soft kernel, or the B30F kernel, which smoothens the texture It also amplifies pixel noise, but not as much when compared to the hard kernel. Now, I'm showing emphysema here, which is closely linked to lung cancer, and we see that kernels are very variable when we measure emphysema. Also, we see that these images come from the same subject with the difference in the CT kernels that are being used to reconstruct them. So we can consider them as paired CT kernels because there's a one-to-one correspondence. Now, when we look at, say, a GE bone kernel image and a Siemens B30F kernel image, we see that there's variability in the scanner acquisition protocol, but there's also a difference in the positional alignment of subjects, which means that there's no one-to-one pixel correspondence here, and we can consider these to be as unpaired CT kernels. Now, we can mitigate this variability in CT kernels through a process called CT kernel harmonization, mainly to ensure that we have comparable measurements for quantitative imaging. Now, when we consider paired CT kernels, what we see is that there's a one-to-one correspondence, so we can do this, but this is very limited to specific pairs obtained from manufacturers. Now, if we consider, say, the multi-center or a longitudinal study where we have unpaired kernels where no ground truth exists, now, this can be a lot more challenging because variability of scanner protocol exists, and also there's a mismatch or there's a lack of one-to-one pixel correspondence here. Now, in recent times, there have been advancements to carry out this unpaired CT kernel harmonization, mainly by treating this problem as a style transfer problem, where you do an image-to-image translation of one kernel to look like the other. Some of the popular algorithms here are the CycleGAN and a variant that we developed previously known as the multipath CycleGAN that was capable of harmonizing across different combinations of reconstruction kernels here. But what happens when we apply these unpaired CT kernel algorithms? Well, for one, we can see that when we're going from a hard kernel that is GE bone to some soft kernel of interest, the lung regions seem to be harmonized to the reference style, but then we see that there is some change in the anatomy here where we can see some inversion in the tissue in the muscle and adipose tissue regions. And we consider this as an anatomical hallucination. This mainly happens because of the distribution matching losses that are present in the CycleGAN model. And when we harmonize images on a large scale, we want them to be correct and intact, and we want them to be anatomically plausible so that we can do further analysis beyond the lung, say, when we want to quantify muscle or adipose tissue that can then benefit in lung cancer. So in this work, what we do is we introduce a tissue statistic loss using multi-label anatomical labels that we obtain from this total segmentator model, and we incorporate them into a multipath CycleGAN in order to preserve anatomy post-harmonization. What we see is that the tissue inversions disappear when we include this, but we're also capable or we're able to do the mitigation of differences in kernels in both paired as well as unpaired CT reconstruction kernels. So the overview of my talk today is as follows. First, we look at what multi-vendor kernel harmonization is, followed by how we can incorporate these anatomical labels into a multi-vendor kernel setting. Then we look at some of the quantitative and qualitative findings of implementing this algorithm, and then we'll conclude with the key takeaways in the discussion. So let's first look at what multi-vendor kernel harmonization is. So we propose a multipath CycleGAN model for multi-vendor kernel harmonization previously. I know that's very big, so let's break it down. Multi-vendor harmonization essentially just means the ability to perform harmonization across different combinations of reconstruction kernels. And we do this by leveraging a multipath CycleGAN model, where we have domain-specific encoders and decoders that I show from the arrowheads, and then we have domain-specific discriminators, where we're able to do harmonization across kernels from the National Lung Screening Trial dataset through this shared latent space. Now, we also introduce this second stage where we incorporate new kernels, mainly to adapt them to this first stage here. So what we do is we freeze the kernels or the encoder-decoder models in the stage 1, and then adapt these stage 2 kernels to this particular latent space, where we're interested in harmonizing the paired kernels to their respective ground truth and the unpaired kernels to a reference Siemens B30F kernel. So how does one particular path look like in this multipath CycleGAN model? Well, we borrow inspiration from the standard CycleGAN approach, where we take this generator and we deconstruct it to have a domain-specific encoder and a domain-specific decoder, depending upon the path of interest. And in addition to the standard losses that are present, we included this identity loss function that penalizes the mean squared error differences on the downsampled versions, mainly because we wanted to preserve the radio opacity post-harmonization. Now, in the backward path, we can do the same thing where we include this identity loss, but then we have a target encoder and a source decoder, and we can perform harmonization in that path as well. And then we have the discriminators that do this process of the adversarial training. So conceptually, we have an idea of what this multi-path cycle GAN looks like and what one path looks like. Let's see how we can incorporate anatomical labels into this to preserve anatomy. So I'm considering the stage 1 that we saw previously, and I'm looking at the Siemens path where we want to harmonize paired kernels, mainly Siemens B50F to B30F. And what we can do is we can replace this identity loss with a tissue statistic loss here. So if we are able to derive anatomical labels using an algorithm like total segmentator or any segmentation model, what we can see is that we can penalize the mean differences on the real and synthetic images using the pre-computed label on the real kernel. Now, why are we looking at the means here? It's mainly because the kernels have their means that are very close to each other. So we find this as an appropriate loss to guide the model in preserving the anatomy. And we can do the same thing in the backward path as well, where we take the multi-label mask on the real B30F kernel and then penalize the differences between the means of the individual anatomical regions here. So the generator that we're using here is a ResNet model. We deconstructed it to have a domain-specific encoder and a decoder with the residual blocks, specifically 9 of them with skip connections, forming the shared latent space that are available for harmonization across all the different combinations that we have. And the discriminator here is a patch GAN model responsible for looking at 70 by 70 patches of real and synthetic images and classifying them. And this then drives the generator to produce images that can then fool the discriminator as the training progresses. So we have an idea of how we can incorporate anatomical labels into this particular model. Let's see what happens on a quantitative and qualitative basis. So when we look at paired kernels, we know that there is a 1-to-1 pixel correspondence, but there is a difference in the texture of the lung parenchyma that we see here. So when we harmonize using baseline models that exist as well as a proposed approach, we see that the style of the lung parenchyma is very similar to the ground truth on both the Siemens and the GE paired kernels. But we want to also look at this in a quantitative fashion. And that's where we look at emphysema, where we want to see how much agreement exists between the kernels before and after harmonization. So before harmonization, we see that the kernels disagree, and I'm showing the median root mean squared error here with confidence intervals. We see that there is a lot of disagreement between them, and post-harmonization, there is agreement between the harmonized image and the target ground truth image, with our proposed models, with and without guidance, doing really well on the GE and Siemens scanners. Now, unpaired kernels are a lot more challenging because there is no ground truth here to harmonize to a reference soft kernel. So we can only take some reference style that we're interested in harmonizing in. And when we apply, again, these algorithms, we see that the style of the lung parenchyma is very, very similar to our reference soft kernel here. But there are some intensity variations here in the form of anatomical hallucinations on images from the cycle GAN and our multipath model without guidance. So again, quantitatively for these unpaired kernels, what we see is that we can match the emphysema score to a reference distribution of interest. And here we have the Siemens B30F kernel shown in the red box and strip plot. And what we see is that on the Siemens B50F kernel, the performance is quite stable across all these models, but there's a lot of variability when it comes to unpaired kernels on the GE and, the GE bone and the GE standard kernels here. And then we want to look at the anatomical hallucinations as well, right? So if we're looking at muscle and adipose tissue regions, we see that the cycle GAN model hallucinates, creating these tissue inversions. We have the switchable cycle GAN, another baseline, where we see the anatomy is intact, but there are some edge effects here in the GE bone image. And then we have the multipath model without guidance, which clearly hallucinates here with a lot of tissue inversions in the region of interest and beyond. And then we have our proposed model where it mitigates the hallucinations post-harmonizing to a reference. And we can also quantify this agreement using dice scores that we obtain between the images before and after harmonization on muscle and adipose tissue. And we see that on muscle, our proposed approach does well when compared to the baseline models when we look at the median dice as well as the range of dice scores. But on adipose tissue, while our model does relatively well in comparison to the standard cycle GAN and the model without guidance, it does fall slightly short in performance when compared to the switchable cycle GAN model. So we've looked at the qualitative findings, quantitative findings, and also the anatomical agreement post-harmonization. Now let's look at some of the key takeaways here. So for once, like I mentioned, there is variability on the GE kernels from our proposed approach. And what we see is that the median scores are lower here when compared to our counterpart model. And we believe that using a mean statistic loss could have resulted in some of the voxels being penalized heavily. And what would have happened is that they would have not been included for the thresholding process for emphysema, which would have resulted in these lower scores. And we can replace this, we could probably replace this with a more robust statistic loss that could help improve our scores. So in conclusion, we propose a tissue statistic loss in the multipart cycle GAN model in order to mitigate these anatomical hallucinations. We see that the kernel differences are mitigated for emphysema measurements on paired and unpaired CT kernels, and post-harmonization, the anatomy is preserved on these unpaired kernels when we include this tissue statistic loss. So with that, I'd like to conclude this presentation. I'd like to thank my advisor. I'd like to thank my friends and colleagues in the Massey Lab, my funding for sponsoring the research, and I'm happy to take questions here as well as the poster. Thank you so much.
Thank you. We have time for a question.
Thank you very much for the talk. I'm sorry, but I didn't really get the motivation behind this approach. What's the real world problem that you are solving with this?
So we want to look at robust analysis beyond the lungs. We know that emphysema is one way that we can look at when we want to look at lung cancer images, where there is a correlation. But we've also seen that body composition measurements can show a lot more correlation with lung cancer. But when we harmonize these images using these unpaired CT kernel models, we see that there are these anatomical hallucinations with these tissue inversions. And the problem there is that you can't really look at a muscle or an adipose tissue measurement there, because that would be incorrect. So we want to preserve this anatomy and then go for this large-scale analysis on like a lung cancer data set that could then benefit whether lung cancer changes and how we can look at lung cancer on harmonized images.
Okay, thank you. Fair enough.
Yeah, thank you.
Thank you very much. We
Thank you.
continue the discussion at the poster session.
Thank you.
And last but not least.
Yeah. So we move to the last talk. So family of deep image prior networks for accelerated 3D late gadolinium enhanced MRI acquisition with enhanced reconstruction. Hasibul Hussein Isham, please come to the stage.
Hello everyone. So it's an honor to be the last speaker of this year's MIDL oral presentation session. So with further ado, I am MD Hasibul Hussein Hisham. I am here to talk about our work regarding the cell family of deep image prion networks for accelerated 3D LG MRI reconstruction. So let's start the problem, what we're doing and what we have done from the very high level overview. So let's imagine a world where you have a heart problem, you go for MRI, and inside the MRI scanner you are staying there for 7 to 20 minutes, and you get your full time data is acquired, and then with some traditional reconstruction your cardiac MRI images are produced. But what if we could lessen the actual acquisition time between maybe 2 to 4 minutes of scan, meaning 1/4 or 1/6 or 1/5 of the acquisition time. So that's the main goal what we are doing, and to be specific, what we are targeting the 3D LG imaging for the left atrium. And the main clinical problem we're trying to solve is basically imaging for atrial fibrosis patients. So atrial fibrosis has been a real clinical problem all over the world. Estimatedly, there are almost 33 million atrial fibrosis patients in the worldwide, and it actually increases the risk of stroke by almost 5 times. And 3D LG imaging is basically one of the most non-invasive tools to visualize and quantify the atrial fibrosis so that we can treat the patients easily. And The standard 3D LG imaging is usually done with ECG and respiratory navigator gating. They're typically done with anisotropic resolution in the vendor machines that is provided by Siemens or Philips or any other vendor. But in this work and what we are exploring in our group is basically trying to come up with some isotropic resolution, and all of the works that will be shown here will be with isotropic resolution that had been done in the scanner in our group. And usually the main problem of the 3D LG imaging is basically they take a long time of at least 7 to 20 minutes for the acquisition. The main problem of this one is basically the left atrium walls are very thin and there are respiratory and cardiac motions involved there. While the cardiac motions can be sometimes useful, but respiratory motions can create some noises in the images, which actually sometimes lead to motion artifacts in the MRI images. And sometimes the technicians are not too, let's say, skilled. Sometimes they cannot optimally place the navigator window, so we need to shift, and that leads to more time. And this is a very common scenario. And for that, we actually get some really bad images. And at the left part of the image, you can see some blurring, but in the right part of the image, you will see almost nothing. There is almost no useful data, and this is due to the non-regular breathing of the patient. So to solve this one, what we were previously exploring is basically traditional compressed sensing reconstruction, which is kind of a go-to reconstruction algorithm for any MRI reconstruction problem, the compressed sensing one. And for the acquisition, what we are doing is basically some variable density sampling pattern acquisition, and we are repeating our sampling pattern in a golden ratio based angle method, where the angle is determined by the number of case space, which is basically determined from the breathing pattern of the patient. Let's say how arrhythmic the patient is, how much rhythmic pattern in the breathing pattern are there. And from the 1D navigator signal, we are grouping within search and acceptance window, and within the acceptance window, we are keeping all the case space data from those time points. And with that data, we are starting the compressed sensing reconstruction. And as you can see in the equation, this is a pretty simple pretty simple compressed sensing reconstruction. The first part is basically the data fidelity part, and there are two more regularization part. The first one is the TV regularization, second one is the BM3D. The TV is used for some local denoising, and the BM3D we are using for some global denoising scenario. And our acquisition is 3D. The sampling pattern you are seeing here is basically in between the two phase encoding directions, and there is another direction which is KX from the readout direction, which is basically through the plane or through the screen here. So that direction is totally fully sampled. We can undersample it anywhere in that direction, and this is the two-phase encoding directions. Our center is oversampled, and in the high frequency area, we are trying to sample the other parts too. So the main problem of that acquisition or that compressed sensor reconstruction is it is a very slow process. It usually takes until 4 to 5 hours to reconstruct the whole image from the full data. And when we're using full data, it also leads to higher acquisition time. So that's a real problem. So a typical solution to that is basically using the deep learning. But the traditional deep learning reconstruction problems, reconstruction MRI that has been gone out has some problems. The first one is basically when we're using supervised algorithm, we need a massive training data set, and that is not really practical for in-house data. When you are imaging in a hospital and you have a very limited amount of data, this is not practical at all. You can use some unsupervised or self-supervised sort of algorithms there. And there is actually a lot of scarcity for public high quality 3D LG imaging data, and in fact, to our knowledge, we haven't found any 3D LG MRI case space data that is publicly available that we can use, might be pre-training or any other sort of stuff. And most of the research have these problems of some retrospective undersampling when they are using some synthetic, clinically unrealistic mask. So what I have already told about this, the readout direction is totally free, so you can undersample it out of anywhere, but the phase direction is not. So undersampling in the phase direction would be clinically realistic. And if I tell about, for example, let's talk about Cartesian undersampling. So for Cartesian undersampling, what people usually do is in the usual literature, what they usually do is they keep the some part of the center which contains the low frequency part, and in the high frequency part, they randomly undersample from there. And in the scanner, in real world scenario, we cannot sample like that. We have to sample in a like regularized manner with some which is guided by some equations. So the solution to the training dataset problem can be is basically using an unsupervised model. And the unsupervised model that we are actually exploring here is basically the family of deep image priors. The original deep image prior came out in 2018 in CVPR. So the main theme of the original deep image prior was the normal neural network model has an inductive bias towards some smooth and natural images instead of noises. So if we start, let's say, with a random noise, and we are trying to compare that random noise with our observed data and then train that network, we will eventually go towards that observed data with some like additional information. For example, you can see some in-painting work that has been done in the original deep image prior. It is also useful in denoising or super resolution problem. So additional to that, the deep image prior idea has been explored in MRI reconstruction too. So this is a paper that came out with the self-guided deep image prior. They actually proposed that idea in that paper. And in this paper, they compared their self-guided deep image prior with the vanilla DIP. The vanilla DIP is basically the main deep image prior that has been proposed in the main paper. The reference-guided DIP, some supervised, and the coherence sensing reconstruction. The reference-guided DIP is almost same as the vanilla-guided DIP. The only difference is the vanilla-guided DIP. The vanilla DIP starts with random noise, and the reference-guided DIP starts with some noise. Starts with some prior information. The prior information being here is basically the 2D IFT reconstruction when you are working with 2D MRI. And here we are working with the main DIP equation. So this is the self-guided DIP equation where you will find that there are two terms involved here. The first one is the data consistency, and second one is the denoiser term. In the data consistency term, the first term AC means is a forward modeling operator, which is consist of three terms. The first one is being the undersampling mask, the sensitivity maps of the multiple coils, and the regular Fourier transform. And you multiply that with the network output. The F theta is the ratio net model that we are using here, and eta being the inducted Gaussian noise. And YC is the observed case-space data that we are getting from the case space. This is the undersampled case space. And the second part is the denoiser part, which is totally different from a vanilla DIP or reference-guided DIP. This is the thing that self-guided DIP has been introduced. And in the denoiser part, they are trying to denoise in every step while they are injecting noise to the estimated complex image, and then they are trying to mitigate that noise in every step with the difference between that network output and the previous iterations estimated image. And this is the ratio net that has been used here. One thing to notice is basically when we are getting a complex image, we are trying to separate this into two channels, and real and imaginary channels, and then passing it to the UNet, which also have two channels to accommodate it, the ratio net model. The main self-guided DIP was using the vanilla UNet, 3D UNet. While we have found that the ratio net works a lot better than using just a vanilla one. Adding some residual blocks actually helps the model. And although it's not here, if we talk about the activation functions also, the main one was using the ReLU activation functions. It has we found out that there is an inherent problem where the ReLU actually suppresses out the negative information out there. So the real and imaginary part can contain some negative values which are suppressed out ultimately by the activation functions. But while we are using JLU or leaky ReLU, we were getting some really good results in terms of qualitative metrics. And the Gaussian noise is inducted after each step of these iterations. And if we talk about the visual results, here we are comparing the self-guided DIP. The vanilla DIP is basically 4 different kind of DIP methods. I've already talked about vanilla and reference-guided and the self-guided DIP. The DIP-TV is kind of an extension to the compressed sensing method that we have described, where we are basically incorporating a data fidelity term and the total variation of the network output. The main hypothesis was to see that whether total variation can help in DIP methods well when this is helping in the compressed sensing algorithms. But we found out that self-guided DIP almost always is getting better results. And we also have a baseline supervised UNet method, which is basically trained on, we are using total 10 data sets in our, it's an in-house data set. We are getting it from the hospital, in the UK hospital. And this is basically the result of one data for the supervised manner while it is trained on the other 9. And there is also, the first column actually contains the ground truth, which is basically the compressed sensing of the full data. And the second column contains the undersampled versions compressed sensing, while the undersampling is done with the half acquisition time, 1/4 acquisition time, and 1/6 acquisition time. So instead of using any synthetic mask over here for undersampling, we are undersampling towards the temporal direction. So we believe that it's a realistic undersampling, because what we are doing is we are trying to mimic the scenario where we will be kept in the scanner for a few minutes or a few minutes more or a few minutes more. So that's where the undersampling comes from. And if I talk about the numerical results, the self-guided DIP actually outperforms the other methods here. And for numerical results, we were using PSNR and SSIM for the quantitative metrics. So if I talk about the future work and some limitations here, one of the most future work is, I was talking about the respiratory and cardiac motion for the 3D LG MRI, but apart from using any search and acceptance window on the navigator signal area, we did not use any motion compensation. So our next immediate work would be using any motion compensation so that it cannot create any noise in the final image. And of course, we would like to check this in the clinical workflow in a prospective setting rather than in a retrospective setting. And if I talk about DIP limitations, there is an inherent DIP limitation, which we also found is basically the spectral bias limitation, which is simply states like that the DIP intends to learn the low frequency contents faster than the high frequency one. And when it tries to learn the high frequency content, it starts overfitting with noise. So if you plot the number of epochs against the PSNR or any other SSIM, you'll find out that especially it will start overfitting with noise at some point. If you look at the graph, the vanilla DIP one, it starts overfitting very early, let's say 100 or 200, after 100 or 200 epochs. And self-guided DIP has been the most the robust according to the noise. And DIP-TV and reference-guided DIP were almost the showed almost similar robustness according to the noise. And I think this is it. Thank you for listening to my presentation. If there are any questions, I would like to address now or at the poster session. Thank you.
Thank you very much. We're actually at time, so we'll go to the poster session for questions. But before we leave, let's give one more round of applause for all of our speakers and for audience for participating. It's great questions. Thank you so much.
Okay, let's get started. Good afternoon, everyone. It's a pleasure to introduce the final keynote for MIDL 25 keynote speaker. So it's Dr. Stephen Eilert, a leading figure in medical imaging, open source innovation, and AI-driven healthcare technologies. Dr. Eilert is the global lead for strategic applied research for medical devices at NVIDIA. That's a long title, Stephen.
It's kind of a Dilbert title.
Okay, that's one-liner. Okay. So he leads efforts to support and accelerate the development of next-generation clinical tools through open-source platforms like Munai, Openverse, and the Holoscan SDK. With more than 25 years of experience in NIH, DARPA, and DoD-funded research, he has played a pivotal role in the development of major platforms such as ITK, VTK, 3D Slicer, and Munai, tools that have reshaped the landscape of medical image analysis and translational AI. He's also an adjunct professor of computer science at the University of North Carolina at Chapel, a McKay Fellow and chair of the Munai Advisory Board. His work spans from intelligent ultrasound systems to autonomous surgical robotics, combining deep academic roots with industry impact. Today, Dr. Eilert will present Munai for the next generation of medical technologies, highlighting how this open source platform is powering breakthroughs in clinical AI and shaping the future of medical innovation. So please join me in welcoming Dr. Stephen.
Thank you for the wonderful introduction. It actually all comes together and makes me feel kind of old. And so, yeah, I've been around for a bit, and I just thoroughly love what I do. And so if one of the things that comes across today, I hope I share with you the enthusiasm that I have for medical imaging and that you all continue that enthusiasm. And it's also a wonderful opportunity to be the last speaker on the last day, right before the awards ceremony. And so I took that as an opportunity to be a little bit creative with the presentation that I'm going to give today. And so it doesn't follow a normal technical presentation format. And let's see here. Do you know where it might be? Thank you. Questions? Oh, there it is.
Yeah,
okay. I got it. Cool. Once I find the cursor. Cool. All right. And so I decided to take a little bit of license with the presentation that I'm giving today. And didn't want to repeat previous presentations since a fair number of you all from Vanderbilt and elsewhere had heard them before. And so what I wanted to focus on, and the theme that's perfect for the last presentation on the last day, is really what's next. All right? And what we've seen is that we're really living in exciting times, really right place, right time by doing AI and medical imaging. And what we saw at today's conference or over the past couple of days is really just a tour de force of what AI is doing to impact clinical care and the research that is going to be impacting clinical care in the near future. So we've got ambient note-taking. Every physician's office that I walk into now, they're like, oh, do you mind if I use AI? Let me explain what AI is to you. All right, and they set down their phone and it starts recording and transcribing notes for them. All right, so the time it took for AI to develop those capabilities of doing note-taking, of summarizing conversations, understanding natural language and so forth, to impacting that clinical performance, granted an administrative performance, but to having clinical impact, which is significant for those clinicians to not have to take those notes anymore, spend hours dealing with them and so forth. It was really almost a matter of months, maybe a year or two in time frame for that to happen. So this is, you guys are at a wonderful place where you can actually think of something today and almost literally tomorrow have it used in impacting clinical care. We also saw this for everything, not just at note-taking, but MRI reconstruction. So at really the foundational level of medical imaging, it's having impact with Daniel Reichert's talk the other day. transcriptomics, radiology, report generation, LLMs, VLMs, the move from RAG techniques to agentic AI. I mean, we just see this amazing evolution that is occurring. But as Danielle pointed out, there's still work to be done. All right, there's still that gap, though. We've kind of hit this wall a little bit, and we need to get past that wall of continuing to impact clinical tech care, and that's where you all come in. But with all of this going on and all of this kind of in the hopper for impacting clinical care, what's next? What is going to be that next big thing in AI, in medicine, in healthcare that you all are going to be part of? When you combine these technologies, or when you leverage these technologies that we're developing individually for X-ray machine here, for pathology there, registration of pathology with MR, as we saw in the previous keynote talk and so forth, really what's going to be next? And so I think we're actually starting to see some of that next already. And this was published yesterday, day before yesterday. Axel Krieger, who probably has been at this meeting before, professor at Johns Hopkins, released this article in which an experimental surgical robot performs gallbladder procedures autonomously. What we're looking at here is AI no longer taking notes, AI not summarizing a report, but AI actually delivering the care. We are looking at AI systems impacting the physical world around them. All right, so it's no longer the system that advises or gives a little bit of notes here and there. It's actually impacting clinical care. So this has really been taking up this challenge, this opportunity for AI to not just be enhanced Google search, but AI to be a companion or an actor, a primary actor, has been fully adopted at NVIDIA. Jensen has this notion that we have evolved from a generative AI phase 2 phases ago to agentic AI, so from RAG-based techniques to agentic-based techniques. That's very popular today. And where we're moving, as shown in that article published yesterday or the day before, is towards physical AI. And this is where AI is now part of our physical world. It's actually influencing, changing our environments, changing our healthcare. It's having a direct impact on our lives. And so this has really been a call throughout NVIDIA to adopt this. And this physical AI, one way of thinking about it, and the way we often talk about it, is that everything is a robot. All right, and so this is a little bit weird to think about, but everything in a physical AI system, you can think of everything being a robot. So clearly there's that autonomous surgical robot. That's AI impacting in that way. But imagine an MR scanner where you put the patient in and you say, hey, I suspect this patient of a glioblastoma, something along those, or early indicators of MS, something along those lines. The MR unit would ideally then, knowing what you suspect, knowing what you're looking for, perhaps scan that patient, identify some early indicators of that, but realize that because of this patient's age, because of how hydrated they are, all these different factors, it'll slightly tweak the TR and TE times or the reconstruction algorithm in order to improve the conspicuity of that suspected MS lesion. Or to point out something completely different. Oh no, it's not as MS, it is microstrokes, and here's a series of microstrokes this patient suffered. You know, those sorts of things we are looking at in that situation. That MR scanner, it's the robot. Or an ultrasound probe that you put down on the patient in order to look at blunt abdominal trauma in the field in an EMS unit. Put down the ultrasound probe, you don't show them a B-mode image. Instead, the ultrasound probe automatically adjusts to the BMI of the patient in order to come up with the best image possible and show you the internal bleeding that is life-threatening for them at the scene of the accident. So everything is a robot, from that MR scanner, the ultrasound scanner, to the hospital system itself. Allocation of resources as they move throughout the hospital so that they're at the right time and the right place in anticipation of emergencies as they come about. As they deliver medicine and deliver food in the hallways, as well as deliver patient care. And so everything is a robot. And you can think of, well, that's pretty stupid. Robots are hard, all right? And so if you look at trying to train robotic systems, you're like, that is just not easy to do. Do we really want everything to be a robot? Well, we acknowledge it's hard, but it brings about this philosophy that in training a system or in delivering a system, where that system, the end product is a robot, is something that is working autonomously and interacting with the physical world. It's no longer that you train something and then you deploy it, but there's this circle, there's this kind of integration of training, simulation, and inference, which ends up dominating how you approach the problem. And that's what I'm going to be talking about today, this combination of training, simulation, and inference, and how they're brought together in order to provide what's next in order to answer that question. So I'm going to talk about building a deployable application and using AI in your application. I'm going to start from the basics, I mean real basics. But then I'm quickly going to go into a new program that we have at NVIDIA that's called Isaac for Healthcare. And this is in the early access phase, and it's something you can apply to become a part of. But it takes advantage of those 3 computers. It takes advantage of the training, simulation, and inference locked together for AI training, for robot training. And then I'm going to talk about what's next, really, which I see as the simulation being key to that 3-computer solution. All right, so again, I'm starting with the basics. And so second thing I would like for you to take from this lecture, first one being a passion for what you do, because what you guys do is so cool. The second thing to take away is CuPy, all right? This is if you do anything in Python, you probably a couple times a day do an import of NP, right? You import NumPy as NP. Well, if you instead substitute that to import CuPy as NP after doing a pip install of CuPy, you're going to see a significant speed up based on the GPU that you have available. You don't have to change any other line of code. It's merely this import line code that changes with the pip install. So it cannot be easier. But if you're looking at, and you have Fourier transforms somewhere occurring within your library, or else if you're doing some matrix operations, singular value decomposition and so forth, using the NumPy library, you're going to find up to 200 times speed up in your performance of your system. So we've been looking at, 1-bit quantization, and I'm a big fan of network quantization techniques, everything along those lines for ways of speeding up your network. Well, another way of speeding up all of your code is just simply do this, all right? So public service announcement. Other cool thing that we have is Holoscan SDK. This is an open source platform that just really makes it easy to do good coding practices, where you define a very modular system and then you pull those modules together in a graph description, graph workflow in order to execute it. And the neat part about this modular description that you come up with is if you happen to have in those modules, if they happen to be GPU-based operators, your data always stays on the GPU and it strings together. Plus that resource contention that often happens for limited memory on GPUs and trying to schedule and run multiple GPU algorithms simultaneously or even in sequence, you often get conflicts occurring. This really helps resolve and manage those because you have this workflow isolation occurring. And so it's a really powerful and simple technique that if you adopt this early on, it allows you to piece together your modules and reuse your modules that I just found very, very handy. And you can specify your modules. I won't go into detail, but this is using OpenCV. On the left-hand side, we have the CLAHI, the contrast-limited adaptive histogram equalization operator from OpenCV running on a CPU. On the right-hand side is the version on a GPU. This is how you implement it to make a Holoscan operator. And then you can just plug in the GPU one or plug in the CPU one or make your other ones. And so it's a really nice way of doing a reusable open source library to build your work on top of. And the neat part about this is if you implement it using this program, if you implement your algorithm using Holoscan operators, this is some work that came out of Nobi Hata's lab at Brigham and Women's Hospital using Holoscan. The grad student developed a way of generating a depth map from a single camera image, all right? And they implemented and developed that as part of their PhD using a laptop and a USB microscope, or a USB camera that he would put down the bronchial phantom that's shown there on the left-hand side. To then run that on some higher-end GPU equipment that is actually has gone through a variety of certifications so that you can run it within a surgical environment. So this higher-end special-purpose hardware using a clinical bronchoscope kind of thing, they were able to just change 2 lines of code in order to have it run on that new system. And so it goes from an RTX, from running on the GPU he had in his laptop, to running on this higher-end system with only 2 lines of code being changed. And so it's a wonderful way of making your research code stay with you without having to change it or rewrite it as you go all the way through to clinical trials, preclinical trials, multi-center clinical trials, or wherever it's headed, or even product. So public service number 3, I guess. All right, and you can use Holoscan from within 3D Slicer, and so it can be running on a separate computer or on the same computer. It uses the open source OpenIGT link in order to make calls in and out of Holoscan, and so it's a really nice way of having these pipelines running in the cloud, locally or wherever, and you can interface them or call them from Slicer then. And there's a bunch of Holoscan operators and reference applications already built out there for you to build upon. And if you want to learn more, here's the QR code. It's going to go away in 5, 4, 3, 2, 1. All right. And so there's a bunch of resources on the web that are out there you can build on. So you've got now your workflow. You're using CuPy in order to accelerate it, and you want to now bring in some AI. Well, in my unbiased opinion, you should be making use of MONAI in order to do that. Wonderful open source package. I'm not going to go into a lot of detail on it, just in an overview, because I'm hoping, all right, show of hands, let's not embarrass myself here. How many of you all have heard of MONAI? Dude, all right, cool. I'm glad I deleted those slides. And so it's great the impact that we're having. And MONAI is a series of 4 different components that are brought together by this open source effort. So I've been with MONAI since 2019 when it started, when I was at Kitware. And it began as this collaboration between NVIDIA and King's College London, and from Kitware I got brought in, and a whole bunch of other, German Cancer Research Center, Johns Hopkins, everyone's contributed to it. It's amazing, and so you have this core set of algorithms that are really built by some outstanding people from around the world. And then it's also been interfaced with annotation systems such as 3D Slicer. We saw mention of QPath and some of the other systems out there for even for pathology and video data in using MONAI Label for AI-assisted annotation. Then there's MONAI Deploy for getting into clinical workflows. MONAI Deploy understands DICOM, and so it allows you to get into a DICOM workflow, receive DICOM pushes, and do DICOM pushes of structured reports as results of your processing and so forth. And then the Model Zoo. And actually, I'm just going to talk about the Model Zoo here. And so where it's being used, what are the Model Zoo components that are out there? Well, there's things for segmentation, there's things for reconstruction, pathology, registration, survival prediction, real-time video. Every aspect of medical imaging is out there and supported by MONAI and available as models in the Model Zoo. And what this has resulted in is 5 million downloads, and this number is old. The reason why this number is old, because it's a week old, but we're getting last month 300,000 downloads of MONAI. We're averaging around 250, 275,000 downloads per month of MONAI. I've been doing open source a long time. This is just absolutely phenomenal to have this kind of impact. It took Slicer like 3 years to get to 300,000 downloads. So it's amazing the impact that this is having, the great uptake that it has. Again, it began as NVIDIA and King's College London, but now 270 contributors from around the world. And so this is, you know, I say you're standing on the shoulders of giants and the best of the work that's out there. And I know a lot of people use NNUnit, another phenomenal open source project. There's ways of getting NNUnit models that you've trained, putting them into MONAI, and then using MONAI's AI-assisted annotation, if you prefer that from a 3D Slicer, to fine-tune that NNUnit model. Or to take that NNUnit model and make it part of MONAI Model Zoo. That's very easy to do as well. GitHub projects, foundation models, so forth and so on. And the neat part is that MONAI is getting caught up by industry. And so a lot of people feel that there's this, you know, you're either open source or you're industry, and that there's a separation. But some of the best contributions to MONAI, and really some of the best contributions to ITK, Slicer, and so forth, come from industry. Because these people need to make products on top of what they're doing. So they make certain their foundational code is bulletproof. So therefore they make certain MONAI is pretty well bulletproof. They've done a lot of testing with this system. And once they adopt it, it's a great pathway for research to get into the clinical workflows provided by those commercial systems. And so what Siemens announced late last year was that with 12 clicks, I haven't tried this myself, but in theory, 12 clicks, if you happen to be running in your clinical system a single VIA workstation, and there's 15,000 of these single VIA workstations out there in clinical environments, 12 clicks, you can have your system in the AI marketplace, your MONAI model in the AI marketplace that Siemens offers to those 15,000 workstations. And you'll be flagged as a research model, so you won't be an official model. You'll be flagged as a research model, and a big red warning, I guess, pops up on the screen saying, hey, this is for research purposes only. However, if you want to then go ahead and do a multi-center clinical trial, you now in 12 clicks, all you have to do to get into your clinical environment, as well as more than likely your collaborator's clinical environment, is do those 12 clicks, and then you're running on your single VIA workstation, as well as your clinical collaborators, your multi-center trial clinical collaborators. To do that in the past would just be an IT nightmare, trying to run software from another institute on another institute's computer as a grad student code, so forth and so on, understanding DICOM, doing the right visualizations. This is just phenomenal, wonderful resource that's available. It was announced at RSNA. And so MONAI, again, all these different components, we're mainly talking about the model zoo because that's what you're going to build upon. One of the cool parts is MONAI's success comes not from trying to reinvent the wheel, but by collaborating. German Cancer Research Center, everyone like that. And now we've got great collaborations with Hugging Face. You can actually upload your models to Hugging Face and then register them and upload your MONAI models to Hugging Face. It'll accept them, and then you register them back on the Model Zoo website for MONAI, and then people can easily download them in their MONAI scripts and run them in their MONAI scripts. So there's this wonderful synergy now that's occurring between Hugging Face and MONAI, and we're going to see more of that occurring. So you don't have to buy into all the MONAI stuff. We get along with everyone. And it's not just segmentation, but it's also Gen AI techniques were added last year, and they continue to grow. We saw one of the papers, I think on the first day, that was talking about simulating X-ray scans, and they were doing like 3048 by 3048 X-ray images. Trying to do the Gen AI for these large images really is a challenge, all right? It adds a level of difficulty. And this one's pretty nice because it's not doing X-rays, and those were huge X-ray images, but it's doing pretty darn big CT images, 512 by 512 by 768, simulations of those that you can generate for arbitrary patients based on guidelines for what body regions you want. If you want disease and tumors presence, all of those kind of text prompts can guide the Gen AI that's out there. Then there's Vista 3D, which again, Total Segmentator is also available in various forms in via MONAI, but this Vista 3D is neat because instead of the 1 by 1.5 millimeter isotropic voxel that Total Segmentator expects for most of its models, this Vista 3D model goes down to essentially 0.5 millimeter isotropic voxel that it's able to use and provide segmentations for, so higher resolution segmentations. All right, and it's not just images, it's even more. So we've bought into the agentic approach that can be supported by MONAI. And so you can have your MONAI agents, your Bratz segmentation technique, the Vista 3D, your NN-UNet model, whatever, available to your VLM. So that if you do a query where you've uploaded that medical image or the EHR data or the EKG data, all of those are also supported in MONAI. If you then ask a question, if you ask a question such as, what tumor is shown in this image, it'll recognize that it is an MRI image, and you're asking about tumors, and so it'll launch the Bratz MONAI trained model that's in the Model Zoo. That Bratz segmentation network will run. You can go ahead and have it calculate statistics on the size of the tumor, the presence, yes, no, and so forth, in order to enrich the context for that query. And then when it answers that query, it's using the results of the Bratz segmentation in order to answer that query. And it says, yep, there's a high-grade glioblastoma, and here's its volume, and so forth. And so it's really a powerful technique, and this whole framework is available within MONAI for you to customize in various ways. And we've got examples of how to do that with a radiological agent and a surgical agent, as well as some commercial solutions with RadVila and CT Chat. And the next cool thing, and this goes to a lot of what we're talking about, and is this trust in AI and moving into the clinic. What we're showing here is reasoning, our chain of thought capabilities that are being added into MONAI. And this will really come out in at MICI as part of the release we're going to have about a week or two before MICI. But in chain of thought reasoning, instead of, and I want to pause this here. All right, oops, so much for pausing. All right, and so in chain of thought reasoning, instead of going directly to the radiological report or discussing findings, we actually have come up with a tool where a radiologist can dictate what they are thinking as they review a medical image. Please pause. All right. And as they review a medical image, and then that whole string of text that radiologist is looking, as well as we give them a pointer and they can point to in the image to say what they're talking about. All of that is fed in order to define the context of the AI system or what the AI system is meant to produce, you know, as far as a Gen AI technique. But this particular Gen AI technique is called chain of thought. And if you look at what it produces, it says, this is a PA chest X-ray image. I begin by, oh man, I need better glasses. I begin my interpretation within the central airways. Trachea and central airways are patent with no evidence of narrowing or deviation. On and on and on. We've shown this text that's produced by this system to new radiologists, other radiologists, and they were like, this is how I teach my med students. This is how I teach people to read and interpret a radiological image. And so this kind of chain of thought reasoning, I think, is very powerful, and we're going to see this evolving more and more within the medical field. All right. And here's MONAI again. It's a group of people coming together. We have special interest groups, our working groups on various topics from ophthalmology to ultrasound. Human AI interaction is MONAI label, federated learning, all of these different groups. They're listed here and on the MONAI website, monai.io website. They're all open to volunteers. We had the kickoff meeting for the ultrasound working group on Tuesday or Wednesday, and we had 107 people registered for that kickoff meeting, and I think we had 40 or 53, something like that, people show up. And so this is a wonderful group, and those people who showed up, it was the head of research for Clarius Ultrasound. It was people from Stryker, from a variety of different ultrasound manufacturers, as well as phenomenal professors from Stanford and all around interested in ultrasound. And so really get involved. If you want to join and influence MONAI's future and learn and contribute, join a working group. They're really active. All right, that's enough about MONAI. So we've started with CuPy. We went then to Holoscan for streaming together and specifying workflow. And if your workflow is AI, you can look towards MONAI to do that. But what we're really here to talk about, finally, the meat of this is, all right, so you've got a way of training your AI system and defining your AI system. But what we really want to do is treat everything as a robot. And as we said, we're going to combine training, simulation, and inference together in order to make this happen. Now, what do we mean by this? What is this combination? Well, this is this combination, this collection of tools, and it's a huge technology stack that we put together to do this. It's called Isaac for Healthcare. And I'm going to give you some links later on, and you can join this as part of the early access program in order to get access to it. It's going to be open source, free for academic and commercial use, real Apache 2.0 licensed stuff, and it allows you to treat everything as a robot, use simulation and inference and training together. And what this means, or what an example of this is sim-to-real learning. What we see here is a robot that's learning how to pick up a needle, but it's actually doing this in a virtual environment, in a simulated environment. And it's not just one robot picking up one needle, but it's thousands of robots training and trying different things in this environment to learn how to effectively pick up that needle without dropping it. And then once you take the best performing of those systems, you can go ahead and install that AI system that's been trained in that simulated environment, install it in a real robot, because you've been in the robot that's in the simulated environment, it's a digital twin of a real robot with the kinematics and so forth worked out. When you then go ahead and deploy it in the real world, you don't have to retrain it, or you have much less retraining that's necessary in order for it to learn how to pick up that same needle or a variant on that needle. So this is showing how simulation is used during training in order to make it so that inference runs, the performance of the system is as accurate as possible. This is an example of reinforcement learning, but you can also do this with imitation learning and a variety of other techniques. And so what you do is you begin with your robot, your sensor, and your anatomy, and you simulate those all within your simulated environment, your virtual world. You create digital twins of your robot, of your sensors, and so forth. And then you use, again, human demonstration is used in imitation learning, where you actually influence that simulated world to show the robot what it should be doing. Or use reinforcement learning given simulated generated data. So given simulated ultrasound, given simulated MR, here's how you should change your TRE and TE parameters in order to make that tumor more conspicuous. And use a reinforcement learning. And then once you have to go to the real world, it takes a much less training data in order to make that happen, because real world training, that's where it's difficult for a robot. That's where it's expensive, costly, time consuming, and so forth. So the more that you can do in that simulated environment, the better off that you are. And again, we created this framework to make it happen. And what we show down here, by the way, is some of our very early results in the lower right. And that's someone with a Clarius ultrasound probe hooked up to a KUKA or Franca, I can never tell, robot. In the simulated world, we taught it how to do an ultrasound scan over a simulated abdominal phantom. And then we see it going ahead and repeating that same scan then in the real world on that same robot, or on that real robot with the real Clarius probe, and the data is being streamed to the gentleman's phone via the Clarius app. And so it's really a powerful technique, and there's a lot going on behind this to make this happen. And the main thing behind this is NVIDIA Omniverse. NVIDIA Omniverse is like the metaverse, but it's good. And so it's a way of simulating digital twins of patients, of sensors. It's been used for industrial design for years, so warehouses, everything like that. It is something, a very proven technology, very capable of dealing with robotic systems, collision avoidance, everything along those lines. It's all already baked into the system. So you create your digital twins, and then you run what's called Isaac Sim in order to simulate all the physics, all the interactions between these devices, between the robot and your simulated anatomy and so forth. And then once you've trained your system in that simulated environment, you take your trained policy and you implement it in the real world, where you have a real motion control system on your robot, and take significantly less data in order for it to run and implement whatever you've trained it for, that subtask that you've automated. And what makes this possible is the fact that Omniverse, you can think of it as a really sterile environment, all right, to begin with. And so that's kind of essentially this top row that I'm showing here, where you've got this phantom on a table, and you've got a depth map and some segmentations from the video. Here we're simulating one video camera that is maybe being used to control the robot. The video camera is looking at this scene and figuring out how to make certain the robot arm is placed in the correct spot. Well, it's a pretty sterile simulation that we have. Well, via Cosmos, we can simulate all these different backgrounds and all these different conditions. So even though it's one environment that you've defined, with a couple of lines of code, you can simulate all of these different scenarios, all these different environments. You can have this robot running in your kitchen. You can have this robot, you know, operating in the middle of a highway, whatever the series of scenarios that you want, or a variety of different OR setups or different hospital room setups. You can make it so that you can control the environment very easily and adapt the environment to these different conditions. So that computer vision algorithm that's used to track the robot to figure out if it's placed on the phantom correctly is that much more robust to changes in its environment, changes in lighting and so forth. And so again, you're doing variations in the world in the simulated environment so that you don't have to go through all those variations in the real world. It's just a wonderful way to train that they've been using for autonomous cars and everything for forever, but we're going to now see this happening more and more within the medical field to train our systems. And we've got simulations out there for ultrasound right now for a variety of different ultrasound devices, where given a phantom that you specified, and maybe it's from a CT scan, you can go ahead and take a Clarius ultrasound probe has been simulated, and you can simulate a Clarius ultrasound probe and the image that you would get out of it with various levels of fidelity. And then again, simulate various types of anatomy, as well as using MONAI, as well as simulate, this is some gated CT that was used to get some data that shows a heart beating within the Omniverse environment. So it's really powerful for training robots under a variety of different conditions. And you don't have to go out and buy a KUKA robot or a Franca or anything like this. If you want to play around with this, I've got one of these sitting on my desk at home. Up in the upper right hand corner, Hugging Face bought a company called Le Robot, or Le Robot, it's French. And it is, they have a robotic arm that you can either 3D print and then buy the motors and so forth from them for about $100, or else they'll sell you one fully assembled for $300. And it's called this SOARM 101, and it's actually two robots. It's the leader, so it's an arm that you can control yourself. You move it around and it knows what movements you forced on it, as well as another one that has a gripper on its end, that's the follower. And so you can do imitation learning that way, or I'll set them up to work together. And so it's really a nice system that you can 3D print, or I'll spend $300 in order to start experimenting with a robotic system. It has a camera in it and everything like that. It's really pretty impressive, and they have hundreds. There is this huge community around this on Hugging Face now that have all kinds of demos and examples and things you can get up and running quickly with it. So that's, if you want your robot to not be an MR machine or an ultrasound machine, but you want your robot to be a robot, $300. All right. So now we've simulated these robots, and we're using, in the simulated environment, we trained these robots, and we did it with a variety of different simulated MR and CT scans using Macy, using MONAI. In order to set this up, we've done the training, and now we're deploying it in the real world, and that's awesome. But that's not what's next. What's next is, I think, really cool, and this is what I'm personally very excited about and spending my time at NVIDIA focusing on. And what's next is really regretfully named digital twin, all right? So digital twin is just a huge catch-all kind of name right now. And so I'm going to begin with defining what digital twin is. Digital twins have been around for forever. So on the left-hand side here, it's the idealized model, all right? So or maybe a statistical model. And this is around in 1967, there was the Tellerac Atlas, right? So you can consider a printed atlas. This is where you look at ACPC points on within the brain in order to normalize a coordinate system for functional sites of the brain that were printed in this book in 1967. To take them and move them from being printed in this book to in your patient's brain so that you would know where to cut and where not to cut. Be afraid, be very afraid. Anyway, and so this is the original digital twin, though, in a lot of ways. Or you can even see Michelangelo's drawings back whenever. Those were kind of a digital twin of a sort. They were guidelines by which you tried to map that information onto your patient in order to guide whatever you wanted to do to them. Where do you place the leeches? All right, and so, you know, if I had to pick a technology, that's kind of like ITK. They did a lot of work with ITK in statistical modeling and statistical models of various organs and shape analysis and so forth. Well, the next level up above that is there's organ-specific models. All right, in organ-specific models, they're maybe a little bit more dynamic, higher precision that you have. They can be registered to your individual, some dynamics again, and it's much better for surgical planning and some surgical guidance. You can think of all the segmentations that we do in the registration with segmentations that we do as within this, this category. And then what I've recently been talking about is all the simulated patients that you have within your surgical environment, within your simulated surgical environment with Omniverse. So that's that third column, that's the virtual patient, and that's where you do the sim-to-real training, where you have all these virtual patients making your robot smarter and smarter and better behaved in the real world with less effort, less risk, and so forth. You can also run virtual trials, clinical trials, and so forth with that. But where it gets really interesting is in this fourth category, interesting in my unbiased opinion again. And this is the multi-system model. This is when you want a model of a heart, and you realize that the heart is connected with the lung, and they have this symbiotic relationship with one another. And additionally, heart has orientation of the fiber muscles within it that controls how it twists when it beats. And the reason why it beats is because it has electrical activity and it has blood flowing through it and all of these other features. And that if someone is really well hydrated, here's the density of the red blood cell count to within their blood versus if they're dehydrated, what's their blood density. All of that, what is their blood pressure, what is their heart rate, all of this is being captured in order to form a much more faithful model of your patient. And this becomes really interesting when you combine this smart robot with a smart, comprehensive representation of your patient. Because no longer is it just that the robot is repeating or guessing what to do next, but this robot has a surgical plan that has a much greater likelihood of succeeding because it's been tried out on that patient-specific model. So these two models that you have are going to interact with one another, and I really see this as the future of healthcare. So that for every patient, every procedure, you're going to be using that digital twin of that patient in order to guide that treatment that's delivered. And that treatment is no longer, oh, I'm going to perform surgery, but it's like, I'm going to begin them on this drug course 2 weeks prior to my surgery so that I can have this change in their blood pressure, or I can have this change in their heart rate, or change in the tissue elasticity, who knows what, dilation of capillary beds. I'm going to have them on this drug course so that then when I go in to do this treatment, here's the outcome that's going to be that much better for them. And I'm going to plan this as perfectly as I can. But when I then go ahead and do that valve implant, let's say I'm doing a valve implant in someone's heart, and I've done all the flow calculations, and I know this is the perfect spot for that valve to be located in the heart. But then I go ahead and I do the surgery, and all of a sudden, it's not exactly right, or things are always slightly different than what you expect. But I put my Doppler ultrasound down, and I look at the regurgitation that's happening at the outflow of that patient, and it's like, it's not what I was expecting. It's slightly different. You run your digital twin. Your digital twin is updated in real time with that ultrasound information, with that flow information, and you know that, all right, this is how much regurgitation I have going on in that valve with the patient laying on the table. What's going to happen when they stand up? What's going to happen when they go for a walk? What's going to happen when they go for a jog? What's going to happen when they go for a jog 10 years from now? Those are questions that we really want the physicians to begin to ask and get answers to via this really high fidelity simulation together with this precise robot to carry those things out as accurately as possible. So it's never going to be perfect, but we're going to be getting closer and closer and improving outcomes more and more. We're no longer going to be looking at ACPC points to guess where the functional sites are. We're going to have something more and more precise and personalized. And the neat part is we're already making good progress towards this. So we talked about Isaac for healthcare. That's the first thing where simulation in medtech is going to pay off. That's training your robots. What I've alluded to is, and talked about briefly, is it also can be used in these simulated environments for device design as well as for clinical trials. There's a company out there that already, you send them the design spec for your device, and they can generate simulated patients and use that device on a variety of simulated patients, help you generate a report, and the FDA will accept simulation results as part of your regulatory application for your device. So right now also FDA and NIH are saying, animal studies, we don't like those as much. We don't want to fund those. We really want to downgrade the use of animal studies. And so does that mean they want more human studies? All right, higher risk, higher cost, so forth and so on. Nobody wants that. They're going to be relying more and more on simulation in order to overcome these reductions in staffing at FDA, changes in requirements, and so forth. And so this virtuonomy company will go ahead, and here what I'm simulating is the insertion of a guide wire into this one vessel, and then that guide wire is followed by the catheter that follows along, that's shown in green as it moves through the vessel. And finite element modeling and flow is being used to calculate then the stresses that are being placed on the vessel wall. So you know, given this rigidity of the guide wire, given this rigidity of the catheter that's following it, here is the impact that it's going to have on this patient's anatomy. You know, is it going to put too much stress on the wall and possibly poke through that wall? And so as you design your devices, virtuonomy will help you conduct these clinical trials in order to come up with the right stiffness for those devices so that they don't have harm on the patient, or are less likely to have harm on the patient. And then where it goes next, again, as I said, is instead of doing this on hundreds of patients, doing this on you. This is what you want to have tested on you before they do it in real life, and that's the personalized medicine. And ANSYS is an amazing company that does simulations for Formula One race cars and mixing tanks and all these other industries, and now they're moving into healthcare. And what they've envisioned in their future is, if you look at the bottom, it's a chat bot that's going on. It's an LLM, and it's running as a NIM. It's a Llama 3 LLM in which they're chatting with it and says, it's going by fast here. It says, all right, what if Mrs. Jones here, heart, has a left bundle block? What would the electrical activity look like? ANSYS is, so you're chatting with it, ANSYS's simulations then go off and run and simulate this change in the electrical activity in order to simulate a left bundle block. And then you see this new electrical activity that's occurring on the heart. And left bundle block happens during transplants and hypertrophic cardiomyopathy addresses and so forth. And so this common condition, how is it going to impact her? And then you can go to what's going to impact her if she is running, what if it's going to impact her if she's doing the groceries, and so forth, or managing the next meeting and getting mad because of not getting the result she wants. All of that can be simulated in different ways. And so ANSYS is working with a variety of companies in order to bring it so that the physician can chat with these simulations and look at various conditions in a very intuitive kind of way. So these simulations are no longer producing images, are no longer producing numbers and heat maps and so forth, but it allows them to discuss clinical diagnosis. That again is AI. Now it's AI interpreting those simulations and converting them into clinical outcomes. So there's this amazing mesh that's going on, again, with AI influencing the training of the system, the simulation of the system, and the inference. And you're cycling between all three of those via chat, if you're a surgeon or whatever, in order to reach better healthcare for your patients. And so this is the future that I'm excited about, this synergy. And you can do this now and play with this now. Omniverse is out there. It's free for development and academic use. And there's already connectors that you can connect 3D Slicer with Omniverse and ParaView with Omniverse. There's the Omniverse kit, which gives you a framework for specifying your own Omniverse application. And so you can come up with your own view of all the information stored about your patient in Omniverse, a view which is specific to a cardiologist, or a view that's specific to electrophysiologists. They're all different views. And you can also do XR. So Omniverse, you can do AR and VR visualizations from it. And you can tie in PyAnsys Heart, which is ANSYS's heart simulator. So you can make things move and interact, or you tie in your robot via ROS. All of this is already available for you within the Omniverse environment. And so it's easy to create. I really recommend taking a look at it. And where I'm really interested is yet another place for AI to impact this whole thing. And this is the last topic, I'm almost done here, is with NVIDIA Physics Nemo. And Physics Nemo, I'm just learning about it myself. It's very much, it's been around for a while, but it's yet a work in progress. And Physics Nemo, their definition from the website is an open source Python framework for building, training, and fine-tuning physics AI models at scale. The neat thing about this is that right now, ANSYS simulations, we're working with them to speed up their simulations, because those simulations for a finite element model of a heart and the lung and everything else that you would want really in this multi-system representation, they'll take hours to run, all right, to do the blood flow, the air flow, the movement of muscles in an FEM technique. But you can train an AI system, and we saw hints of that in presentations over the past couple of days as well. You can train an AI system to approximate those physiological processes, the physics that are behind the blood flow and so forth. And so Physics Nemo has the foundation models that are based on neural operators, Fourier operators, graph neural networks, and so forth, that you can then fine-tune those models that instead of being water flowing, they fine-tune for blood flowing with particles mixed in within the heart. There's demonstrations out there that show in a couple hundred lines of code you can simulate blood flowing through an aneurysm so that you can plan the coiling of an aneurysm. And again, this is work in progress, but it does CFD, FEM, electromagnetics, and a variety of variants on those. And you can mix your PDF approach to optimizing your physics solver with the AI, where the AI maybe gives you an initial approximation, and then you use your physics solvers in order to fine-tune that, or vice versa. You use your physics solvers in order to get you close to the answer, and then AI gets you the rest of the way. And that combination makes it real time. Actually, they are estimating that they can do a heart rate simulation in 75% of the time of an actual heart rate beating. And so it's faster than real time that'll be possible. And so when you go to simulate your 100 patients in your virtual world to train your robot on how to guide a snake-like robot for a catheter into the heart in order to do an ablation or an autonomous replacement, TAVR procedure, replacement of a valve, you'll be able to simulate that robot moving in the heart at a faster speed than real time, so that you can train more models, you can try different variations more, you can run more of these AI systems simultaneously, and your model will get smarter faster because you'll have a better physics engine, a faster physics engine running it. And so again, we see this synergy between AI now running the models faster, the physics faster, as you're training an AI system for a surgical robot or whatever that's using an ultrasound probe, which is AI enabled. And you know, all of this kind of constantly going on and interacting with one another, where I'm just very excited about the future that we have with this. And then having all of this produce an AR, VR environment or an LLM that you can chat with from a surgeon at an intuitive level. It's just all of everything that you saw over the past couple of days brought together via this framework. So as you can tell, I'm very excited about this. I do see it as a great way of going for streaming the data together in order to give you that LLM with the cardiologist, AR, VR with the surgeon, and so forth. And, oh, one too many. And so hopefully that inspires you all, and the last lesson that I had to share. Thank you.
Thanks, Stephen, for like open, I guess, eye-opening.
Yeah.
That's the right word, eye-opening presentation. We have 10 minutes for Q&A.
I wanted to leave some time.
Yeah. Questions? Perhaps let me start.
I can talk more otherwise. So if you don't ask a question,
Well,
I'm going to talk
this
more.
one will introduce some tension in the discussion, so hopefully. So open source platforms and code like Omniverse and Monai are empowering research in academia and also commercial products.
Yes.
How do you see the balance evolving between open science and proprietary development in healthcare AI?
Sure. I'm a big fan of proprietary software as well. I just want to make that really clear, because there is nothing personal, but there is a gap, and there should be a gap, between kind of the academic research version of an algorithm or of a method and so forth, and then that commercial version. And that is a non-trivial gap, and that will always be there, all right, to get integrated. We're trying to break down that barrier and reduce it more and more, but there's always going to be that level of difference that exists between them for the foreseeable future, all right? And so I really value that there are people out there willing to take it that extra mile, as opposed to saying, hey, I got my PhD, I'm done, I'm now going to go after my next grant or my next job or whatever. And so, you know, I think that there's just this inherent separation between them that isn't bad, but we want to make it so that that transfer as easily as possible. And open source makes that transfer as easy as possible. It does not make it so that it reduces or eliminates the chance for commercial opportunity, but actually it speeds the ability for research ideas to make it into commercial use. And so, and companies to succeed with less development funds themselves, because they're building on top of open source as opposed to having to write their own DICOM query and retrieve system. And so it's really a wonderful relationship between the two. I don't see it as competition. We should all really get along. It's in everyone's best interest for them to use. And if they find a bug in the open source, they being commercial groups, they should fix that bug so that in the next version of the software, they don't have to fix the bug again, right? And then you get that better version that's fixed. Or if they've got a registration strategy that's in their method, that's FDA approved right now, one of the biggest risks and expense for a company is, should I go ahead and use new algorithm B that I just saw in some journal article and replace my current registration framework method with this new registration framework? All right, it used to be without open source. That means completely re-implementing that technique. Maybe your implementation isn't exactly right. You know, all of these challenges you can spend as a small business trying to figure out if you should use this new registration strategy. That's a high risk, high expensive thing. And then going ahead and submitting FDA reapproval of your system using that new registration algorithm and so forth, very expensive, costly, risky. If everything is done using open source, it also allows existing businesses to pull in these methods all that much faster. And so I love it all around.
Thank you. Yeah, go ahead.
Yeah.
Stephen, thank you very much for this great talk, and it's nice to see that you moved to the light side. The question that's on my mind is, so recently we started to discuss from kilowatts to megawatts, and this brings completely new problems, like we need cables like that now.
Yeah.
What's your view on how we should address the energy footprint we are causing by all of this, and probably also maybe you have been instructed what's NVIDIA's view on all of this?
Yeah, and listen, this is not my area of expertise, but I'm going to do a quote of some company things. If you look at the power consumptions per compute that is available, in the systems, we are constantly looking at, NVIDIA is constantly, and everyone is constantly looking at ways of reducing the power requirements for these GPUs as they come out. And so, it is this pull that's happening for faster and faster compute, which typically does mean more and more power, but then that's also more expensive. And so if you come up with something that's a whole lot faster, but also much more expensive to run because it has more power, no one's going to buy it. So, it makes business sense for us to address those power consumption. And if you look historically, NVIDIA personally has been very successful at driving down the energy requirements per compute. Now, as a society, I think we do have to, there is those considerations that we have. Just because that compute exists and is out there, we have to be cognizant of the demands that we are placing on it. And I forgot exactly what the statistics was, but I think it was Sam Altman was saying that OpenAI spends like $1 million a day. I'm totally making that number up, all right? It spends $1 million a day processing the word please. All right, and so just by phrasing your query to ChatGPT with "please tell me whatever," you're contributing to the loss of $1 million, and it's probably more than $1 million of tokenizing the word "please," processing it, not placing attention on it, and so forth. So I mean, it feels rude to do that to the ChatGPT, but don't say "please." All right, just get to the question, but that also carries over to your own research. And if you look at it's these small things that I think all of us can contribute to as a society, saying, listen, I know this AI model is going to fail. Should I really just go ahead and run it on my computer for 3 weeks because I don't have anything else planned? Maybe say no. All right. So there's the big business aspect of things, and there's market forces there, but then there's also our aspect of things. And there's many other layers in between. And so I wish I had a magic wand to address it, but everyone's working towards it, and we can all do something.
And my answer would be foundation models, right?
Yeah. And if something's been done, build upon the stuff in the model zoo rather than starting from scratch, those sorts of things. That's a really good point.
I think that's very helpful. Thank you.
Thank you. Yeah.
Hi, thank you for the talk. I'm Ege. I work in the surgical domain, so it was very exciting to see you now also moving into this area. You really emphasized simulation as the main way of kind of generalizing to these applications, simulation and then sim to real. My personal feeling is that foundation models are also going to play a huge role, because now we also have models that already know what the rough phases of a surgery should look like, and we are getting at a point where they even know what roughly they should do. How do you see this playing a role in this generalizing to surgery? Like sim to real, for sure, but how about foundation models? How do they play a role here?
Always start with the all right, well, yeah, sure, okay. Always start with the foundation model. And so I should have, Bernard was spot on with that. If there is a model that is at all within the domain, you can significantly reduce your training time. You have to realize that they aren't the end all to be all. And also you have to realize the impact that fine-tuning a foundation model can have. NVIDIA research spent quite a bit of time with Vista 3D to make it so that if you fine-tune it, it doesn't forget what it's already learned. And so these foundation models are both kind of a blessing and a curse. You have to really be thorough in your testing of any system, but in particular, don't neglect testing those foundation models, because it could have performed exceptionally well, and then, I'll just fine-tune it a little bit and then release it. Well, your little bit of fine-tuning could have completely degraded its prior performance scores. And so it's a little bit of a challenge, but if you do it right, they're definitely the way to begin, but they're not, the complete solution.
Thank you.
Cool.
One last quick question.
Okay. Thank you for your excellent talk. It allows us to see the future world. And I have a small question about it. I want to know, how does the Omniverse achieve low latency data synchronization.
Okay.
Yeah.
Yeah. And so Omniverse has a couple of, it's just software, and so you can run it in a variety of different ways. And if you pair it with, you know, and here I don't want to put on a sales hat, but if you pair it with the right, you know, hardware and so forth, it's super low latency. We've spent quite a bit of time, NVIDIA smart folks have spent quite a bit of time trying to make it so that you can actually do sensor reading, sensor value straight to the GPU. So there's ways of going straight from HDMI sensor digitization with the AGA board and others, and go straight into the GPU, do all of your processing using the Holoscan SDK with your data staying on your GPU, and then driving your Apple Vision Pro or whatever, and I'm making that up, I know it works for Quest, there we go. So driving your Quest from the GPU memory directly. And so everything stays on the GPU, and you're looking at 10 milliseconds of processing time for that software when run on the right hardware on the AGX and IGX systems. But if you go ahead and run on your laptop, it's going to be good, but it's not going to have all of those benefits. But the neat part is that's all behind the scenes. And so if you use Holoscan, if you use Omniverse and so forth, as you move from your laptop to this higher end hardware, it'll take advantage of it and have these capabilities without you having to do anything. So it's low latency if you want it to be, and if you have the right hardware.
Yeah, maybe we could remote our work at home. Future,
exactly.
future.
Yeah. And so
Thanks
it can be
for
in the
your
cloud and others local and so forth. Yeah.
Thank you.
Thank you.
Okay.
Thanks,
Thank you all
Stephen,
very
for
much.
the great talk. Okay. Good evening, everyone. We have come now to the final chapter of MIDL 25. Welcome to the closing ceremony here in the beautiful Salt Lake City. Over the past few days, we have explored exciting advances at the intersection of medical imaging and AI, shared insights, built connections, and strengthened this vibrant research community. So before we officially close the conference, let's take a moment to reflect, to celebrate, and to recognize the people and the work that made MIDL 25 so special. We are grateful to all of you, attendees, speakers, reviewers, participants, and however you participate in making MIDL 25 actually come to life. In this closing ceremony, we'll revisit some highlights, thank those who contributed behind the scenes, and look ahead for the next MIDL next year. The scientific heart of MIDL was so dynamic as ever, with an impressive range of research topics presented across oral sessions and keynotes and poster session. And this year's program blended innovation as well as applications, clinical application, translating those tools to the clinical practice. So we saw exciting work of foundation models, multimodal learning, responsible AI, generative AI. So beyond the research itself, there is a really energy in the room that is undeniable through conversations, really tough questions, and basically interdisciplinary discussions everywhere. So here's just a glimpse of the scientific discussions that defined MIDL 25 and a field that is clearly evolving towards a greater impact. The oral session this year showcased the cutting edge of research in medical imaging and deep learning, from foundational models to actually deploying this in clinical applications. We have packed rooms with questions and lively discussions that spilled into the hallways also, which is a clear sign of thriving, engaging community. The poster session also brought the energy with packed boards, lively conversations, and spontaneous idea sharing at every turn. It was great to see researchers at all levels deep dive into each other's work and spark collaboration. So thank you all to all the poster presenters for bringing your work here and bringing also your enthusiasm. Of course, none of this would happen without the real engine behind every scientific conference: food. Coffee breaks and lunch turn it into a research meetup with desserts and keeping everyone well-fed and well-connected. MIDL 2025 was defined by 4 remarkable keynote presentations, all centering on clinical impact and methodological innovation. Dr. Arbel introduced causal and uncertainty-aware deep learning for predicting disease trajectories and treatment responses, pushing us towards truly personalized imaging in neurological conditions. Dr. Ruckert explored how AI is transforming radiology. He emphasized privacy-preserving and explainable imaging tools that support clinicians in areas like cardiovascular MRI. Dr. Russo showcased how multimodal learning that bridges high-resolution pathology and MRI with more accessible tools like ultrasound can enable early cancer detection, especially in low-resource setting. And finally, Dr. Eilard has emphasized the transformative role of AI in healthcare, shedding light on the future of AI as an integral component and collaborative component of every hospital. These talks collectively showcase MIDL's dual strength, pushing the boundaries of deep learning methods for medical imaging, as well as ensuring that these technical advances make a path towards a meaningful and practical applications in the clinic. While the technical program was the heart of MIDL, the soul of the conference was found in the conversations, many of which happened over food, music, and shared laughs. The welcome reception, the gala dinner gave us time to connect more personally, to meet new collaborators, to make new connections, to reconnect with old friends, and enjoy a moment of celebration together. These informal moments help build the kind of community that the MIDL board had a vision to build. One of the most unforgettable moments of MIDL 2025 wasn't in a hall or on a poster session, but it was up at the Natural Museum of Utah watching the sunset over Salt Lake City. A quick update on the publication process. All full MIDL papers will be published in the Proceeding of Machine Learning Research, continuing our commitment to open access and high visibility dissemination. We will soon begin processing your camera-ready submissions, and you will receive your final edited version shortly after that. In addition, a selection of outstanding papers will be invited to submit an extended version for a special issue in the MILBA journal. As a new initiative this year, MIDL 25 introduced travel awards to help support in-person participation with a focus on PhD students and early career researchers. We awarded 16 awards of 500 each, aiming to reduce financial burden and helping emerging students share their work and engage with the community in person. So recipients have been notified by email, and we would like to thank our sponsors for helping launch this important new effort. We are incredibly excited to share that MIDL 2025 has been awarded an NIH R13 grant to support travel awards for our participants. In fact, this news has happened, or we received this news in the middle of the first day of the conference, but we opted to delay this is the closing ceremony to give you the new news. So this funding will allow us to significantly expand our efforts to make MIDL more accessible, especially for students, and we will offer more travel awards in the coming weeks. We extend our sincere thanks to NIH for recognizing the value of MIDL community and the conference and helping us grow. We would like also to highlight one of the core values of MIDL, reproducibility. Thanks to the efforts of Attila Simko from Umeå University in Sweden, we tracked and analyzed the availability of code across all accepted papers. And we are pleased to share about 3/4 of accepted papers included a public code repository. This is a major improvement from last year. Only 12 papers had either private or empty repositories. That's only 11%, down from 30% from last year. So please fix that. This shows real progress and commitment from the community. And if you're curious about the process, the criteria, the guidelines, you can learn more on the MIDL board website. And once again, a big thank you to Atelier for leading this important initiative. We're highlighting here the top 13 papers that achieved outstanding reproducibility scores based on the criteria from the MIDL reproducibility checklist. We thank the authors for setting we thank these authors for setting a high standard and contributing to a more open and verifiable research culture at MIDL. We hope to see even more like this in the future editions of MIDL. We would like also to take a moment to highlight a truly special thing here. This year, one of our accepted papers was led by a first author who is still in high school. It's an inspiring sign that the next generation of scientists and engineers is already thinking deeply about AI in healthcare. MIDL has always welcomed ideas from across disciplines, institutions, and also experience levels, and this is a wonderful example of how future-minded MIDL's community is. Of course, none of this would have happened without an incredible effort from many, many individuals and teams behind the scenes. From organizing logistics and reviewing papers to running sessions, ensuring everything ran smoothly, getting caffeine to everyone. There's a huge team behind this MIDL 25. We would like to take a moment to recognize and thank everyone who helped bring MIDL 25 to life. Let me start with the organizing committee. It has been an honor and a true privilege for Tolga, Ron, and myself to serve as general chairs this year. Together with the entire organizing committee, we have worked hard to make MIDL 25 both scientifically rigorous and community-driven, and to create a meaningful and welcoming environment here in Salt Lake. We would like also to extend our sincere thank you to our outstanding program committee, Ron, Lisa, Shen, and Jan. Their dedication, expertise, and careful reviews were essential in shaping a high-quality scientific program. We deeply appreciate their time, their thoughtful attention they brought for every single submission. We would also like to thank the organizers of two important events extending beyond the main MIDL program, the Doctoral Symposium and the upcoming post-day workshop. The Doctoral Symposium offered a valuable platform for early career researchers to share their work, receive feedback, and connect with mentors in a supportive setting. So thank you, Shika and Ricardo, for making that happen. And while the conference formally ends, hopefully in 20 or 15 minutes, many of you will be participating in tomorrow's post-day workshop. So we thank Bennett in advance for his efforts in curating what promises to be an engaging and focused set of discussions. These events expand the impact of MIDL 25, and we're grateful to everyone who made them possible. We would also like to give special thank you to the incredible team at SCI here at the University of Utah. From registration, venue logistics, to AV coordination, signage, catering, and so much more you can't even imagine. This team provided phenomenal support throughout the planning and the execution of MIDL 25. They have their attention to details, responsiveness, the behind-the-scenes problem solving, helped everything run smoothly and allowed us to really focus on science. We are deeply grateful for their dedication and professionalism. A big thank you goes to our amazing team of volunteers of students, whether it was managing session logistics, guiding attendees, troubleshooting tech issues, or handling last-minute needs. You were the friendly faces that kept MIDL running smoothly. Your energy and professionalism and willingness to jump in whenever needed made a real difference, so we are truly grateful for your support. We hope this experience was as rewarding for you as it was impactful for the conference. We'd also like to extend our sincere thanks to the sponsors of MIDL 25. Your support helped make the conference possible, from enabling student travel grants to supporting social events and to helping us provide a high-quality experience here in Salt Lake. We deeply appreciate your investment in the advancement of medical imaging and AI and in fostering a collaborative, open research community. So thank you for being part of MIDL 25 journey. We would like also to give a big thank you to our area chairs who played a critical role in ensuring the quality and rigorousness and fairness of the MIDL 25 review process. They managed it, their thoughtful decisions have shaped the scientific program that you have experienced this week. We are deeply grateful for the time, for their care that they brought to the conference this year. A heartfelt thank you goes out to all our reviewers. The review process is the backbone of any academic conference, and your thoughtful, constructive, and timely evaluations ensured that MIDL 25 upheld a high standard scientific rigor. Apologies for the super tiny font, but this year we have 283 reviewers contributing to a total of 544 reviews. Every single paper has received at least 3 reviews. And that was only possible thanks to the dedication of our reviewers. We also want to thank our session chairs for the oral presentations. You help it keep the session focused, on time, and engaging, facilitating thoughtful discussions and ensuring each presenter had the opportunity to share their work clearly and confidently. Now, we have reached to one of the most anticipated moments of the closing ceremony, and you guessed it, it's the awards. So drum roll, please. Each year, we take a moment to recognize outstanding contributions to the conference, from exceptional papers to dedicated reviewers and inspiring presentations. And with that, I'd like to hand it over to Ron, who will walk us through this year's awardees. So Ron, the stage is all yours.
Thanks, Shireen. It's a great pleasure to now present the awards. First, I'll start by recognizing the outstanding reviewers. The criteria for outstanding reviewer was quality of the review, timeliness, responsiveness during the discussion, and each of the people whose names I'm about to show you were nominated by the area chairs. So if we could just recognize the outstanding reviewers shown here. Okay, next, Best Oral and Poster Awards. The criteria were quality of the paper and quality of the presentation. We're going to start with the best posters. So the best poster committee, what we did was the program committee shortlisted the number of posters to make it a manageable process, and then the 6 individuals listed here helped with the selections, so thanks to them. And then for the best oral paper candidates, we shortlisted the 9 regular papers in the oral sessions based on the average scores provided by the reviewers, and then each presentation was attended by Yan Zhang and myself, and we scored them on a series of categories such as clinical relevance, quality of the presentation, clarity, and organization, and so forth. So now I'd like to start by awarding the runner-up for the Best Oral Paper Award. So the runner-up for the Best Oral Paper Award is PRISM High Resolution. And okay, great, you're here, excellent. So let's see, how should we do this?
I don't know.
What's the best way? Up
Yeah, I
here?
guess so, yeah.
Okay. Must you hold that?
Perfect.
Thank you. Okay, next is Best Oral Paper Award, and that goes to the authors of MedVAE. Okay. Next is the runner-up for the Best Poster Paper Award, and that goes to HIEGNet and the authors of that paper. Oh, great. Now all I have to do is find the right certificate.
You also take the other one.
You want the other one? Okay, I'll give you a different one.
Oh.
There you go. And last but not least, the Best Poster Paper Award goes to the self-supervised synthetic cerebral vessel tree generation using semantic sign distance fields. Excellent. Come on this side.
Okay. At MIDL, we are proud that this is more than just a once-a-year meeting. The annual conference is, of course, the main component, the centerpiece, where cutting-edge research is presented and the community gathers in person. But what makes MIDL truly special is what happens around and beyond the conference. Through community-driven efforts, members of our field are shaping the future of medical imaging with deep learning, from organizing sessions to launching new initiatives. We have also seen the success of MIDL challenges, which foster benchmark data sets, shared problems, and collaborative progress. Our young researcher events provide mentoring, networking, and visibility for early career scientists, ensuring the next generation feels included and empowered. And with ongoing online events, we are keeping conversation going year-long. Together, these efforts show that MIDL isn't just a conference. It is a growing, evolving community. And now, to share a bit more about one of the most dynamic parts of that community, I'm happy to hand it over to the Young Researcher Board to tell us more.
Hey, so I won't take up too much of your time because we're all at the end of the last day, but I just wanted to highlight some of the events that we have coming up, particularly the MIDL Young Researcher Showcase. So any young researchers in the room, I know there's quite a lot of you who might be in the early stages of your PhD or doing a master's or something like that. Feel free to submit an abstract. The details are on the MIDL website under the Young Researcher tab. It'd be great to see you there, and hopefully we can put on a great event. And what we do at the Young Researcher Board wouldn't be worthwhile if it didn't take into account the views of the Young Researcher community. So we really ask for your feedback to make the Young Researcher Board what it is. So if you have any suggestions of what we can do better, what you need as young researchers in this community, feel free to email us, or you can provide the feedback via the form linked here. I also want to say that there's an opening, or there's going to be some openings for the Young Researcher Board. So at the end of this year, I'll be stepping down from the Young Researcher Board. So if you want to apply, you can send a short CV and some of your motivation for joining the board, and we'll look over those and we'll appoint new board members. It's been a great opportunity to really network with the community, so if that's something that interests you, then feel free to go ahead and apply that. We'll put some more details on the website in the coming weeks that can give you a little bit more detail about what the role will entail and things like that. And I'll hand you back over. Thanks.
Okay, as we wrap up MIDL 25 here in Salt Lake, it's inspiring to look back at the incredible journey this community has taken from Amsterdam in 2018 to Montreal, London, Lübeck, and beyond. MIDL has grown not just in size, but in impact, diversity, and global reach. Each year, we have built on shared goals, advancing deep learning with medical imaging, fostering reproducibility, and creating a truly welcoming research space. This year, we have continued that legacy in Salt Lake with outstanding contribution across science collaboration community. And now we are thrilled to announce that MIDL 2026 will take us to Taipei, marking the first time the conference will be hosted in East Asia. We can't wait to see how the community continues to evolve and grow in the vibrant, tech-forward city of Taipei. We hope many of you will join us next year and help shape the future of MIDL. To give us a preview of what to expect, I'm very pleased to hand it over to Sheng Fu from Shangguang Memorial Hospital, who will introduce us to the plans of MIDL 26. Sheng Fu, the stage is yours.
Thank you for giving us the opportunity to host MIDL 26 next year in Taipei. And this is our organizing committee. We hope to do our best program for next year. And Taipei is a vibrant city in Taiwan, and we give you some of important dates, and we want to have our pre-day meeting on 7th of July next year, and then please remember the deadline for the paper submission will be 5th of December this year. And Taipei is in the middle of the East Asia, so it's very convenient with lots of flights from anywhere from the world. And we have a very flexible visa policy, so no worry to enter Taiwan. And we also in Taipei we have a very good MRT system to connect you everywhere. And certainly in Taiwan, we have lots of East Asian and Taiwanese destination for you to explore. Certainly, we won't let you down about the food in Taiwan. So we will have a very good gala dinner in our Grand Hotel. So see you next year. Thank you.
And with that, we come to the end of another incredible edition of MIDL. Over the past few days, we have seen groundbreaking research, passionate discussions, and community that continues to grow stronger, more collaborative, and more globally connected. We want to thank every one of you for making MIDL such a success. Thanks for attending, thanks for speaking, thanks for connecting. Whether this was your first MIDL or your seventh, we hope that you leave here inspired, supported, and energized to continue pushing the boundaries of AI and medical imaging. Safe travels, stay in touch, and we look forward to seeing many of you in Taipei next year. So thank you and goodbye from Salt Lake.